it's only the instructor who's going to be talking, and if it's the instructor who's infected, then we're done for, correct? So they added another exhaust fan here, which helped. Okay. So I think that is what this summarizes. So you can see that for larger rooms where there are a lot more ceiling fans, there's a chance of this vortex trapping air from flowing through. So you have to have a directionally different blowing of air that has to come from, say, a pedestal fan, right? So that this wall is broken and you can let air flow through. So I'm just skipping because time is of short. I want you to do more hands-on. Now coming to the hostel common room, again we had large windows with different levels of fans on. Here the kids came up with a very interesting solution, right? So they had four exhaust fans on the four ends of the room. Okay. And when they played around, so the first thought was, let us switch on the middle fans so that it forms and these exhaust fans can pull out air. I mean, seems to be a good idea. But what we saw was that that trapped in a lot of air. So when you have exhaust and fan none are on, then it was very high. Then they switched on all fans. It helped to bring down the average air residence time to 58. Maximum air residence time and average air residence time, right? And when they switched on the middle rows, very strangely, it took up the maximum air residence time up quite a bit, seconds maybe. And then they tried the outer ones, right? That brought it down further. So then what they said was a very energy efficient way of doing it is to alternate fans in this pattern to break up the air residence, bring down the air residence time, because you're not using a lot. So if you look at it, when all fans are on and when only these alternate fans are on, we're actually doing better, right? So it's a very smart way of breaking up these recirculation zones, and this is something that the kids really enjoyed doing, right? So what is the kind of conclusions I'm trying to bring out here is multifold. First, let me talk about technical aspects. Most of these rooms, we did about 4 lakh elements maximum, and simulations were doable in a couple of hours with the air residence time, if in fact minutes. And that was because a complex problem, if you seed these particles and track them, they become very difficult. So with something called air residence time, just solving an additional scalar equation, you are able to run this simulation in a very manageable way, look at very much interventions and place exhaust fans. By the way, some of these exhaust fans have been placed. Huh? Okay. So the other thing is they were able to also try different fan simulations. So you either do a actual rotating frame, which is computationally expensive. The other way of quickly doing it is for a fan, just create a pressure jump surface and give a pressure jump across, and that was able to bring down. Maybe the swirl component was slightly missing, but that doesn't really alter your air residence time significantly, is what we have found. Right? So they were able to kind of measure and see how these affected the outputs. Um, and what we saw was that takeaway for you in terms of ventilation, optimize your air residence time first, because ACH can, trying to talk about air changes per hour as a homogeneous block can easily be met. But it is the air residence time which is very tricky. It is totally upon recirculation zones and breaking it up. Okay, so that is something you can first look at. Huh? As far as interventions, even in your own homes are concerned, ceiling fans definitely help. If it's one or two fans, it doesn't create a vortex in itself. It helps to bring down break these recirculation zones. Prop doors partially open or have holes in them, levers which will enter fresh air, or a reverse fan which will pull in fresh air, especially near instructor regions where people tend to talk more. Always, you have a high powered exhaust fan in one region doesn't help. Smaller powered exhaust fans, 2 3 different locations in the room, will help break up these recirculation zones. So with that, I will. This is kind of repeating itself. Uh, Larger rooms, big classrooms, try thinking about pedestal fans as well. So all of these are very low in cost, right? And you can do CFD simulations, have your students do CFD simulations to exactly take this forward as a class project as well, which is what we did. So with that, I will acknowledge all these students who have contributed to it, and thank you. I will take questions now. That's 1 hour. Am I audible? Is complete silence? Oh, we've hit 100 participants. So I'll stop presenting. Yeah. So any questions, please feel free. Okay. So if there are no further questions, what I will ask you to do is please do the hands-on session, and I will be very interested to know if you will take this back to your courses, to your students, and make them try and do these simulations. They become really engaged in trying to understand how ventilated their own rooms are, hostel rooms or something of that sort. Payal or Evan, whoever can take on now.
Yes, ma'am. Pile ma'am will, I think, do that. Okay, so thank you, Janvi ma'am. I think
Yeah.
Pile ma'am is a little bit busy with the YouTube thing. So on
Okay.
YouTube, the session is live for those who are asking for the YouTube link. Yeah, so yeah. So now we'll move on to the demo and hands-on session. Just give me a minute, okay? I'll just open all the files first.
Yeah. By then, I'll just answer 1 or 2 questions in the chat box, right? So, there's somebody asking, Mr. Wade is asking, are we considering the effect of students sitting in the room? Yes. We did do some really professional simulations where we had people breathing out CO2. So, we had a CO2 tracer as well. But at this, I mean, for a student trying to do these simulations for a class project, that probably will not be computationally viable. But we have done it. Yes, we have done it.
Now, how do we model that breathing of people in the room?
So, see, the idea about it is essentially you're looking at the CO2,
Yes.
because most of these building people have CO2 sensors. Essentially, CO2 is a surrogate for how old the air is. So you just model a mannequin with a mouth, with a CO2, you know, tracers, scalar transport equation, species transport with CO2, and a breathing person's numbers are available. So you have that come out. That essentially how you model CO2. Okay.
Thank you.
Yeah. Uh, so, Mr. Harish, you had asked if the numerical simulation is validated, right? Yes, we for the washroom simulation, we did a quick session where we had agarbatti lighted up in a couple of places, filled the entire room with smoke. And of course, we did have high tech cameras, but what we tried and did was download an app which is a PIV, low cost PIV thing on the phone, and we were tracking the agarbatti's movement. And we were able to map onto the speed of the agarbatti smoke with what the simulations were predicting. We also had a high-tech downsized part of the room with the PIV sensor with lasers and all of that. That also mapped on. So yes, we have validated numerical simulations with experiments. Can you suggest some learning resources from basics? I think any CFD would do. Unfortunately, for ventilation per se, from the CFD perspective, we didn't have a book to go to. This is all what we learned by rolling our sleeves up and kind of breaking the problem. Yeah. Evan, sorry, I'll allow you to take it forward.
No, no, it's fine. Okay.
Just a second. Can I? Am I audible?
Yes, ma'am.
Okay, that's great. So in the morning also I was going on introducing Professor Janani, but then I realized that I lost connection. So thanks a lot to you, ma'am. So
Thank you, Payal. Yeah,
yeah,
thanks.
so we actually missed your introduction, and I really don't want to miss it. So before we end this lecture session, I just want to introduce you. I mean, just so that the participants know who was giving the lecture. So Professor Janani Sri Muridharan is an associate professor at the Mechanical Engineering Department at IIT Bombay. She has completed her PhD in Mechanical Engineering Department from IIT Madras. Prior to this, she has done her BE in Mechanical Engineering, followed by a master's in Aerospace Engineering. She was a researcher in the Mechanical Engineering Department at Imperial College London until December 2015. Both at IIT Madras and at Imperial College London, she has been a part of several multi-phase heat transfer research projects. At IIT Bombay, Professor Janani specializes in the areas of computational fluid dynamics, multi-phase flow and heat transfer, biofluid dynamics, and phase change phenomena. Her current research interests are in the areas of boiling and bubble contact line dynamics, blood flow modeling, and CFD-based ventilation studies. So that was a brief introduction about the Janani ma'am, and she used to be the principal investigator of the CFD team of FOSSEE, IIT Bombay, and she is a patron now. And for every support and for every guidance, we always reach out to her, and she's always there to help us and to support us. So thanks a lot to you, Janani ma'am. Yeah.
Thank you, Payal.
It's a
Thank
pleasure
you.
to welcome you in this FDP, and I'm sure I could read the chat also that all the questions are being answered, and they were very attentive during your talk. Though I was firefighting with my team here to reload this LDAP problem that we are facing at IIT Bombay. I hope the problem is resolved and we will have a smooth session ahead today. Okay. So with this, we are ending this lecture session now, and we are moving forward with the hands-on session. This session will be handled by Evan Fernandez from FOSSEE team of IIT Bombay. Over to you, Evan. Evan, you are muted.
Yes, sorry. Yeah, so Janani ma'am, before you leave, could you share the PPT, because a few of them were asking about the uh, files that you have shown. So the files itself can be downloaded from our website. It's just that the PPT, whatever data you showed, they wanted to refer to that.
Sure. Okay.
Okay, thank you, ma'am. Yeah. Yeah, so I'll share my screen. Okay. Can someone just confirm whether the full screen is working?
Yes.
Not yet. Full screen. At least I cannot see the full screen, but I can see the tiles.
Yeah.
I can. The
It's
full
visible.
screen is visible. Yes.
Okay, okay, fine. Yeah. So, wait. Before starting this session, what all of you can do is under day 4, I've uploaded all the files. So under day 4, go to CFD and ML, and you can download the ventilation template. So again, there are two files. One is for OpenFOAM 9 and one is for OpenFOAM 2412. So this will be a demo session and a hands-on session. So first I'll explain in a demo session what we are going to do. And I'll talk about the ML code also. The ML part or the machine learning part, you don't have to run it because that's a little bit complex and you will require some data and all that. I'll explain that in a while. So the ventilation part is a simplified version of all the cases that I will show you so that you can run it during this session. Okay, so again, depending on the version that you have, so there's one for OpenFOAM 9 and there's one for OpenFOAM 2412. Download accordingly whichever version you have. Okay, you can download the remaining files as well and keep it if you want. You can refer it to when I'm showing things. Okay. So once again, good morning, everyone. And today we'll be seeing what exactly is air residence time, how to simulate that in OpenFOAM. And we'll also look briefly about machine learning because in the past few years, machine learning and AI incorporation into CFD is quite trending. So we'll look how can you do that again in OpenFOAM and separately as well. So these are some of the applications of air residence time or even HVAC, you can say. So in clean rooms, you require to have air circulation done properly. So again, you have clean rooms, air circulation. It also varies in reactor designing. So in case you have a nuclear reactor, in those cases, you don't want the air to get accumulated in one corner or in one particular area within that whole reactor. So for that very reason, you do air residence time analysis. You can also do air change analysis. So based on that, you can define an AHU. So for people in HVAC will know what an air handling unit is and how can you define how large you require that machine to be depending on the air change hour that you have and the room size itself. So that's what Janine ma'am was saying about heat loading and how ART is related to ACH. So that's all the applications for ART. So now the first case that I will demonstrate is the CFD room that Janine ma'am showed. So in this is actually the lab that we sit in. So the CFD lab of FOSSEE, this is the exact model. So the mesh for this one is quite fine. That is why I'm not I'm saying that you can run it, but it will take some time. So that's why a simplified version of this exact room is shared with you in the ventilation template. So we'll see how to run that. So before that, I will just demonstrate how can you go about setting up your ART foam, running first your flow simulation, then introducing the scalar and solving for the air residence time. And lastly, once you do enough of simulations, you can also incorporate all this data into a machine learning program. Okay, so this is your problem statement and these are your inlet and outlet areas. So the door and the AC will behave as an inlet, whereas your exhaust is your outlet condition. So all these are mentioned in the mesh and in your boundary files. So you can check that in the files itself. For the simplified version, I have done it using block mesh and topo set. So you can change the exhaust part. Just put the highlighter on. Yeah, so you can change the position of this exhaust in the simplified version. So that is the whole reason of giving you a simplified version, because we want you to change this distance. So you can change it in the X direction, in the Y direction. So based on that, you can also see how does it affect your air residence time. If you want, you can also change boundary conditions like inlet velocity for the door and for the AC, and you can check how does your ART change based on that. So for this case, we have kept an inlet boundary condition for the door, AC, and an outlet condition for the exhaust. Okay, this is a video of the exact same simulation that I was talking about. So in this one, as Jenny ma'am was saying, that if you keep some particles or you leave the particles at the door, how does it roam in your entire room? That is what your air residence time is doing. So how long does your particle take, or it's there within your system? So in this case, you can see that now this was for a dual exhaust case. So you have two exhausts on the top. So over here, there's one more exhaust. So you'll see that once these particles reach this exhaust, a few of them have been exhausted out of the system, whereas a few remain within the system. So again, depending on how long does this particle stay, you'll have some recirculation zone. So again, based on how you set up your exhaust inlet, your recirculation zones will change. Based on that, your ART will also change. Okay. So this is the workflow in ART. So for your CFD analysis, first we'll just start with that. So for CFD analysis, you're using OpenFOAM, obviously. So for that, you will first analyze the flow. So as ma'am said, that you can, we are using a steady state solver, steady state turbulence solver. So in this case, we're using simple foam with the turbulence modeling of K epsilon. So we are doing the flow analysis first to initialize the flow. Okay. Once your flow has reached a steady state or near steady state, uh, uh, when it's reached close to steady state form, that time, while this is running, you can also compile your solver. So the ART form is not a generic solver in OpenFOAM. It is a modified scalar transport form solver. So when you're running your flow analysis, you can side by side compile your solver. And once the flow analysis is done, you take the velocity file from this. So your last time step velocity file that is there, you take that and you plug it into the ART form, because for your ART form, your scalar is going to be based on your velocity. So the velocity is already initialized and you're just introducing the scalar. So that is what your ART form is doing. So for that very reason, it requires the flow analysis final U file. So we'll be taking the U, plugging it into ART and run the new solver that we have just compiled over here. Okay. Once the ART analysis is done, you can do this for different combinations. So in this case, what I will demonstrate now, you will see that they have varied the exhaust location. So they've kept it on the left wall. Go back. So you can see over here, the exhaust has been varied on this wall, the back wall, and above the AC. So they've changed the direction of or the location of the exhaust, and they've seen how does that affect your ART. So in total, they have done around 24 simulations, out of which around 19 were kept to train a machine learning model. So in this one, you're using an artificial neural network. It's really simple. So an artificial neural network in simple terms uses some set of data that you already have. So in this case, we have the CFD data. You train it on that, and then you use some other data or additional data that. So in this case, we use 80% of the data that you've got from the CFD to train the model, and you use 20% to test the model. So in this case, out of those 24 simulations, 80% was used to train this ML network, and the other 20% was just used to train to test it whether your analysis is similar to the CFD analysis or is it diverging. So you got an accuracy of around 81 to 90%. So that's really good for an ANN. Okay. Again, we'll see this in the upcoming sessions. Okay. So don't worry about that. So the flow structure, okay, so the case structure for the flow analysis is as follows. You have in the zero folder, you will have some additional terms because you're solving for turbulence. So ideally you would just have velocity and pressure. But in this case, since I said that we're solving for a turbulence model, the K epsilon model, so that is why you have these additional files. You also have a Y plus file, but again, you can ignore this. This is just because you're solving for a turbulence model. That is why this file is there. You have an all run file. So in case you want to just run everything with just one command, you can do that. And the mesh itself, that has been created in ANSYS Fluent. So you have this mesh that is created in an external mesher, and we can then run it in OpenFOAM. So I'll show you how to run external meshes in OpenFOAM as well. How can you import those? So that is why you have the .msh file. Within your constant folder, you have again your transport properties and turbulence properties. And within your system, now you'll see that there is no block mesh file because we have created the mesh in ANSYS, so that file is not required. So you can delete that. The remaining files remain the same. So you have control dec, decompose par. So again, I'll briefly talk about how to decompose a case as well. I think Manzil spoke about it yesterday, but I'll just explain it once more. And then you have foam data to fluent dict. So again, this will just hold off all the data that is there on the ANSYS mesh. And you have FE schemes, FE solution, residuals. So again, I'll show you how to plot your residuals as well. So in case you want to check whether your solution is converging or diverging before it actually does, you can always check that using your residuals. Yeah. So before going to this, I will show you the case file structure that we have. So for this demonstration, I have this MFTH room case. Now this case is done by one of Janani ma'am's student. So again, he was Dipanjan Das. He was also a master student. He has done the simulation. So all the files that you have over here are done by students. So you can always check that. It's also available on the website. So you have three files as you saw. So you have the velocity file. You have the actual artform.c file. So this is your solver file. So you have to compile this. And this is the air residence simulation file folder. So within this, you're using artform to run the scalar part. So let's open the velocity. So just now what you saw was the velocity. So you have 0, you have all of these files, you have the system constant, and you also have the mesh file. Okay, so first what you will do is I'll show you how to run the simulation first, just for the flow part. Okay, so once the flow is done, then we'll go to compiling it as well, compiling the solver. So I'll just open WSL, increase the font size. Yeah, hope it's visible. Inform 9. And now if you create a mesh in a external software, in this case ANSYS Fluent, and you want to import it, so you can do for Fluent, this is okay. So for Fluent, you can type Fluent 3D mesh to foam, and then you have your file name. So in this case, it is mfht cfd lab e2.8m.msh. Now again, if you want to export your mesh file as a .msh file in ANSYS, you have to make sure that it is in the ASCII format, not in the binary format. So again, under options, you can check that out. So under options, you have to change that from binary to ASCII. Otherwise, OpenFOAM won't understand what is your mesh file. Okay, so once you run this command fluent 3D mesh to foam, and the mesh file, you can run it. It will run. So over here, it will say that your meshing is done. It will also show you all the properties that are there within your mesh. Okay, so now if I open it in ParaView, I'll just do touch foam.foam. Okay, so now I'll just open the file manually. Okay. Okay. 1 minute, I'll just see if it is clean. Yeah. Okay. So just for parity, just bear with me if you're not able to see the very small text, because when I'm trying to rescale it, that time it's giving problems. Okay, so this is your mesh. Okay, I'll show you the mesh itself. Sorry. Okay, so this is a pretty fine mesh, and I'll include all the patches so you can see what's actually going on. Yeah. So over here you can see we have the door. Then on the right hand side you have the air conditioner. And then you have the exhaust over here. So now this is a single exhaust case. There is also a case with dual exhausts. So now in this case, what they've done is they've moved this exhaust and they've seen how does it affect your air residence time. So for the flow analysis, first you will solve the velocity. Okay. So to do that, go back to the terminal. So once you've created your mesh, you can do Fluent 3D mesh to foam. And after that, you can directly run simple foam. Now, simple foam, if you just run it simply by like this, it will take some time because it has to run around 5,000 iterations. So that is where your decomposition comes into play. Okay, just 1 minute. Okay. Okay. Yeah. So just a second. Okay? Sorry for. Yeah. Sorry for the disturbance. Yeah. So as I was saying, that if you want to decompose a case, for that you have something known as a decompose predict. So that is under your system, and you have decompose predict. Okay, changes back to okay. Yeah, so this is your decompose predict. So you have something known as number of subdomains. So this is how many how do you in how many pieces do you want to decompose or break your entire domain. So in this case I have 4. The method over here, you have a method that is simple. So if you're using the simple method, you will have to specify the coordinate systems. So for simple, if you want to break this entire domain into 4 pieces, so you have to specify the XYZ coordinate. So in the X direction, I want to break it into 4 pieces. You can also change it to 2 2. So meaning the 2 means that in the X direction, I wanted to break it into 2, and in the Y direction, I want to break it into 2. So you will have it broken, something like that. So your decomposition in simple term is giving all the work to different processors within your system. Okay. So how do you see, how can you define this number? Okay, because everyone has a different laptop. So based on the laptop that you have and the actual physical processor that you have within that, you have to check that. So here, so you can check how many cores you have on your laptop by doing ls cpu. So again, this is the command ls cpu, and when you type ls cpu, it will give you all the information about your processor. So in my case, I have an Intel 12th Gen i5 processor. So that has 6 cores. So that's a CPU family model. And over here, you'll have thread per socket and core per socket. So these are the two values that you have to check. So in cores per socket, this is the physical cores that are present on your system or on your processor. So you can think of it in this way. Say you have a classroom full of students. Okay. Now that classroom full of student is your laptop or your processor. Now, if you want to assign some work, if say you are the only person or you have a classroom full of students, but you are doing all the work, so the load on that one person becomes a lot, and you have to then, and then the work will also take some more time. So what you do by decomposing is you distribute that work to different sections in your class. So if you have your entire class, you break them into 4 groups and you assign each of the group one of the work. So that way all of your work is distributed and it becomes quicker. So that is what you're seeing over here in your CPU. Okay, so in your LS CPU, it will give you how many groups you can create before your actual system crashes. So in my system, I cannot exceed 6 cores because it will just crash Windows. You have to leave one core for Windows itself. If you're on a Windows laptop, that's one downside of this. So Windows itself will require one core at least to run some processes in the background. If you're opening some tabs or something like that, it requires one core free. So you can use up to 5 cores. Now in your laptop, it may happen that you have 8 cores. If you have a workstation, then it ranges from 10 core, 12 core, 24 cores as well. So again, this value changes, and based on this, you have to set the value in your decompose particle. So in my case, I've set it to 4. Another thing to keep in mind is that just because you have that many cores doesn't mean that your work will always be fast. So once you have assigned that work to a group of students in your case, you will have to collect that data and then stitch it all together. So that is where again your reconstruct power comes into play. So if you have a lot of if you have many students in your class and you've made say 10 to 15 groups, you will also take time to collect all of that data. So in case you have a powerful workstation, you're running it on say 30 or 60 cores, again when you're reconstructing your entire simulation back again, it will take time. So you have to keep in mind that always having more cores doesn't mean that your simulation will run faster. So just keep that in mind. It's not that just because you have more it will run fast. Okay, so over here in this case, I am distributing my domain into 4 equal parts. You can also use another method called Scotch. So again, there's method simple, there's method Scotch. Now your Scotch method will automatically determine how many or how you want to distribute your domain. So in my case, this room that is there, it's a simple cube. Just a second, I'm sorry for that. Extremely sorry about that. Yeah. So as I was saying, for this case, you also have another method called Scotch. So that method will directly determine how many or whatever number you specify. So in this case, 4. It will determine where it requires more or less cells. Okay. So the simple method, I have defined it physically. So now it has to distribute my entire domain into 4 equal parts. Whereas in Scotch method, say if I'm doing something as like a flow or a cylinder, and if my mesh is very fine closer to the cylinder, so it will assign or it will break down the entire domain closer to my cylinder into say 2 or 3 parts. And for the entire or the rest of the domain that is coarse, uh, it will assign it 1 core for that. And whereas for the finer areas, it will assign 2 or 3 cores more. So that is what the method does Okay, so you have different methods. You have simple, you have hierarchical, you have Scotch. So depending on that, you can choose whichever one is appropriate for you. So in this case, I am keeping it as it is, simple and right. So now when you want to run it, so the very first thing you have to do is create your mesh that we've done. Now you do decompose par. Yeah, so you do decompose par. You can hit tab to fill out everything. So once you do decomposition, okay, it gave me an error saying that y plus is not a field. Okay, so let's delete this y plus for now. Without it also it's fine. Just clean the case. Boom. Clean tutorials. Okay. So now again we will do fluent mesh to foam. So our mesh is created. Now we will decompose the domain. Okay. So as you can see that it has decomposed my entire domain into 4 processors. So processor 0, 1, 2, 3. So now each of these processors have some work to do. And it also defines how many cells it has allotted to each one of them. Now, since it was using the simple method, so it has assigned it almost similar. Only the last one has 1 cell less. But if you use Scotch method, it will directly assign based on however close your cell is, or however close your or fine your mesh is to an object. So it may happen that in that it may assign like 23 cells over there, whereas over here it has 23,000. Okay, so just keep that in mind. So once you've decomposed your case, now you're going to run it in parallel. So for that, you can do mpi run space dash or hyphen np, that is your number of processor, and then you specify the number of processor. So this number has to correlate to the one that you set in your decompose part. So in this case, I have mpi run np4, so because I have 4 processors assigned, and then you type in the solver name, in this case, simple foam space, and then you type parallel. Okay. Now this last word that is there, parallel, that is very important in this command, because even if you run mpi run dash np4 simple foam and you forget this parallel run, your simulation will run, but it will again run only on a single core because it does not know that you have to run it in parallel. So keep in mind that you always type in this last word as well. Otherwise your simulation will just run on a single core and you might think that it is running in parallel. So when you type this command, it should start running. Now, previously, when I would run my simulation without decomposing it, it would directly start logging all the files over here. But now, since I have done decomposition, it has now these additional files known as processor. And within the processor file, it will start logging all of the files. So in this case, once it hits 100, it will log a file. And again, once I do this, you have to reconstruct it as well. So now this is for the flow. Okay. So I already have this case run. So I'll just stop this. This is just for demonstrating how to run the case. So once you've run your flow, I'll just take the run case from here. So I have this velocity file already run. And if you notice that it's starting from 0, then it has 3100, 3200, all the way up to 5000. It's not starting from 0, 1, 2, 3, 4, 5. So there's a reason for that. Okay. So under the system folder, if you go to your control dict, so in this control dict file of yours, so you have application simple foam, start time, end time, you have your delta t as well. There's something known as purge write. Okay, so in this case, I have set that purge write to 20. By default, it is always set to 0. So what this purge write does is that this you can also use if you're running any steady state simulation and you're only interested in the last files. For transient simulations, you will require all your files because you want to check it over time. But in a steady state, it's not the case. So you can set this purge write to the value that you want. Now in this case, 20. So what it will do is when my simulation is running, it will only save the last 20 files. So in this case, if you count all these files till 5000, it will be 20. And how it will work is now if it has created a file from 0, say all the way up to 20. And then from 20, when you're logging the 21st file, it will log the 21st file, and then it will delete file number 1. So every time every time it's logging a new file, it is deleting a file from the back. So that is how your purge write works. And again, if you have storage problem, you can always use this. So in this case, I have set it to 20. You can also set it to just 1 because we're only interested in the last file. Okay. So now since we are only interested in the last file, we have ran the velocity, and then you can go into the last time step file, and you have to copy this velocity and plug it into the ART form file. Okay, that is your air RT, not the ART. ART is the folder that has your solver. Okay, so that brings us to this part. Okay, now you have ran your simulation for the flow. You've got your velocity at the last time step. It's almost steady state in this case. And once you've got that file, you want to plug it into your ART form. But before that, OpenFOAM needs to understand that there is a new solver named ART form. If I directly just run ART form, it will throw an error. So for that, you have to compile your solver. So in this case, you will have these files. So these are the primary files that you will always have for any solver modification or any solver development. So you will have a make file that will have your file and options. Yesterday, Mansell explained it in detail. He opened each of these files. So I'm not going to explain it too much in this case. So just to explain what exactly is happening here, you have the make file, you have ART form, and you have create fields H. So in this case, we are modifying the scalar transport form to the ART form. Okay. So this is the equation for your scalar, for your actual scalar, and this is your generalized one. So in this case, we have just substituted S instead of phi, as Jenny ma'am was explaining in her PPT as well. And this is the OpenFOAM version, or the simplified version of what this equation is. And in OpenFOAM, how does it look? Okay, so in this case, you can correlate it with FVM DDT, so DDT of S, and then again phi and all of those things. And over here we have the sources. So you'll see that over here we also have a diffusion term, but in this case, since we're solving for time and time does not diffuse, we'll keep that as 0. Whereas your sources, as Jenny ma'am explained, that since you're solving for time, and if you take dt by dt, it cancels out and it becomes 1. So that is the reason why it is 1 over here. And these are also some of the steps that I have added in the PPT itself. So if you want to compile it or make some modification from scratch, you can refer to this. It explains what exactly each of these files do. So to just help you out with compiling the solver, so this is one thing that if you have already downloaded the template file, you can do this. So you can go into the file named ART. So I'll just get out of this file. So I'll do cd dot dot. And then I will enter the ART form. Okay, so this is my ART form. So if you see, I have make the .c file and the header files. Okay, now in this case, I'll just show you what exactly does these files have. Okay, so the header file will have your S. So if you see the actual scalar transport form file, there will be everywhere it will be written as T. So we're just substituting T for S. The rest everything remains the same. And if you scroll down under transport properties, you will have an additional term. So there's already DT in the original file. So we changed it to DS, that is your diffusivity. And the sources, we have named it as sources S. So again, it will require you to add one source value for it. And same goes for the .c file. So the beginning remains the same. It's just that the equation under the FV scalar matrix has changed. So where you can see that if you see the original code, it will be T over here, DT and T. So over here, everywhere we substituted for S, and since the equation requires the source part, so we've added sources S. So again, sources S, it will try and search it under your transport files. Okay, so this is the file. So what we'll do is first, we will compile the solver. So to compile a solver, you have to first clean any pre-existing files that were present. So you can do w clean, and then to create a solver to compile it, you can do w make. Okay. So now, if you get any errors during this process, it will show it in bright red, and it will also tell you in which file it is. Okay. So in this case, I'm not going to show you that because already we don't have a lot of time just to explain the solver part. We also have to do the hands-on. Okay. So if you get any errors, it will always show you in red. It will give you the path to it. So you can always read the terminal and go to that. So in this case, we have compiled a solver. It's working fine. It hasn't thrown any errors. So again, I will again repeat this. So you can clean a solver. So you can, before compiling a solver, you always clean any pre-existing files that may cause problems. So you do w clean for that. And to compile a solver, you do w make. Okay. So once you do wmake, you'll get this text in the terminal. So now your ART foam solver has been compiled. So now we'll go back and we'll go to the actual file in which we are running the ART foam file. Okay, so that file is named as air RT. So in this case, it's air residence time. That is what the file's name is. So now since I have it run already, so it will show some additional file. Now in this case, it's just the files. And the one that I'm showing you over here is the run file. So what you do is you plug this velocity. So this U file is taken from your velocity file. Okay. So if you open it, you will see that it has all the data that has been shared at time step 5000. So it will show you over here the time step also from which I'm taking it. So at time step 5000, these are all the values for velocity. Okay. So we are going to plug this velocity, and we also have the scalar itself. So this is a scalar that you have. So in this case, we are not giving any initial velocity to it. So that is why the inlet values, and at AC it's 0, outlet it's 0 gradient, wall it's 0 gradient. Another thing that you will see that you have to make changes is in the constant folder. So in the constant folder, you have the transport properties. And under transport properties, by default, you will have dt, that was diffusivity, but now we also have the source term. So in this case, the source term, we are setting it to 1. Okay, now some of you might ask that since the source term is getting cancelled out and you just have 1 over there, why not add 1 to the equation itself? So we've tried that. Whenever you add a value or a number to the equation over there in the source code, it throws an error. So that is why we have manually said that look up the source term, and then over here in your transport properties, you can manually change it. It's also necessary in case you ever want to change it in the future, your source term or your source value. You can change it over here rather than opening the code, making the change over there and recompiling it. So that is one added benefit over here. It's just for convenience that we've added it into your transport properties. Diffusivity, by default, it was always there in your scalar transport form. We just changed it to ds. And since this is a time related term, so we have kept it to 0 because time will not diffuse. Okay, so now you have all these files. You've set your diffusivity to 0, you've added your source term, or you've added the value for source as 1. You've set up your scalar or your source term, your scalar in this case, put the boundary conditions for it, and then you've copied your velocity file to your air RT file. Okay, now you have to run this file. So again, similar approach. So now this is the file that I have. I hope it's visible. If it's not, just let me know. Just clear this once again. And yeah, so these are the files that you have. So within, okay, so I think the PPT I've added it. Yeah, compiling again, I've added these two values as well. So you can use it for making or cleaning your solver. And this is your air residence time folder. So under this, you have 0 and S. So that is the files that are over here. You also have the same mesh file. So you'll have to again compile your mesh, make sure that's working fine, and then put in all the properties for your scalar and your velocity, and then run the case using air residence time. Okay. So this is again your U, that is your initialized flow. Okay. So this is the ML part. So before going to that, let's run this case. Okay. So again, first you do the mesh. So you do fluent 3D mesh to foam, and then you type in your file name. So I'm doing my meshing first. After that, if you want to decompose the case, you can do that. If you want to run it on a single core, if you are running on a single core, you can directly type ART foam and it will run the simulation. But in this case, the simulation on a single core will take close to 30 minutes for this particular case, since it's a very fine case. But for the template file that you have, it will run in 5 minutes. Again, the mesh is quite coarse, so you cannot expect very good results on that. So, and it's also a scaled down version, so the dimensions will be completely different for that. So this is for running it on a single core. If I want to run it on a set of cores that I have in parallel, so I can do decompose par. Again, I have 4 cores, so it's again distributed against among 4 phases, among 4 processors. And then I run the command again the same, mpi run -np, number of processors 4. And in this case, my solver name is ART foam. And then I type parallel. Okay. So once I start running it in parallel, it will run all the way up to 2000 iteration. So over here, the delta T is 0.01. So that is why it takes more amount of time to run. It will take longer as well. And the end time is also quite large because we want it to stabilize completely. Okay. So since I already have this run, I'll just show you the results for it. So if you were to run this case, the actual case, which is done by Dipanjan, it will take you around 10 minutes for the flow, along with that 30 minutes or so with the ART part. Okay, so keep that in mind. It will take you a good 40 minutes just to run this case. So since now this case is already run, so I have these files. Okay, so I have a .foam file as well. So just open this and show you what we're trying to do. And how can you actually see the scalar value? Okay. Run case, air residence time, foam.foam. Yeah. And about the post-processing part, in the afternoon session, we have one complete session dedicated to post-processing. So don't worry about that. I'll show you how to post-process this as well during that session. So for now, again, you can check using VTK blocks, color, and I can switch on all these patches. So you can see the door, window, and the AC where they are. Okay. So now since it's overlapping against the internal mesh, that is why you have some distortion, but otherwise it's fine. Okay. So now if I want to view what is happening within this, I can decrease the opacity first. I'll just switch off all these patches for now. I'll switch it on later. So now you want to check the air residence time within this entire room. So there are two ways you can do it. You can trace the entire streamlines. So you can also check the air residence time like this. But again, this is in 3D space, so you won't understand what is happening. So again, there are two ways you can do it. You can either view the streamlines and see where the recirculation zone is happening. So this is the point source. I'll show you again in the afternoon how can you change or do post-processing like this. Change this to 5. Yeah. Change this to 1000. Yeah. So this is your door. I'll just switch back the patch on. So the patch. Yeah. So you can see that here you have the door, here you have the AC, and here you have the exhaust. Okay. I'll also switch on the patch names if I can. Okay, I can't do that in this version. Fine. So this is just the 3D view or streamlines in your entire case, what is happening. So from the door, you can see, I hope you can see, switch it to solid color.
Yes.
Yeah. Reduce the opacity down more. Yeah. Okay, so in this case, I'll just switch off these patches. It's causing confusion otherwise. Yeah. Okay, so this is your door over here. If you see closely, you have some flow entering your room, then it goes on top and it hits the top ceiling and then it comes back down. Over here, you also have the AC. So there is another flow happening over here. It's coming, it hits the floor and then circulates back up. And in the end, most of the flow is going out this single exhaust. Now in the dual exhaust case, you would also have some flow happening over here. But now since this has just one exhaust, this is what is happening in this particular case. Okay, now this is just the streamlines of what is happening. If you switch this to velocity, now since it is set to scalar or the air residence time, so this is your velocity. So where you have the highest velocity. Here, since we're giving negligible inlet velocity and same for the AC, it's not that high. Okay, so this is your velocity streamlines for your entire domain. Now, if I want to just see the air residence time at a particular distance. So in this case, I want to check it at a height of 1.3 meters, 1.6 meters, or even at 1 meter. So I can take a slice So this is a slice. You can add it in the Y normal. So in this case, and I will set the height to around 1.3. Normal height also I'll set it to 1.3. It's fine. And then I do show plane. So it is going to show me the plane. Click on apply. Switch off the show plane. Okay, delete this. Create a slice on the object itself. 1.3, 1.3. Apply. Yeah. Okay, so in this, I'll just switch this off. Yeah. So now you can see at a distance of 1.3 from the bottom, you have this type of flow. Okay, so I'll just switch it back to this. So this is your door area. Okay, here you have the door over in the front. This is where you have the AC, and this is where you have the exhaust in the back. So at 1.3, you can see that the air residence time is around 771 or 710. Yeah. So that this is in seconds. Okay, so you can see that over here, since your circulation, so you can switch to velocity as well. So velocity, it won't be able to see that much. So over here you can see that you have some zones that are having circulation over here, and then the air remains circulated over there only. It's not exiting the system. So in that case, you can check your air residence time in your particular room. So again, this case is it's for the lab that we sit in. So you can also check for the same if you have your entire room, or in the room that you are currently sitting. You can check the dimensions. It does not have to be accurate. It can be an approximation, and you can then run the simulation or run the same solver and see how much whether in the place that you are sitting the air is fresher or it's there for some more time. So that can be done. Okay, so this is one way to just check the air residence time. I'll also show you a way to check the direction of the flow. So you have something known as a glyph, and in this case I will orient it to the y direction, to the velocity. Yeah, and I'll scaling factor, I'll reduce it a little bit. Yeah, scaling area I'll put and see. Okay. Will not add a scaling area, otherwise you won't be able to see what is happening. Yeah, so you can see in this case, this will give you the direction of your flow. Now this is oriented for velocity. So from the door, you can see that the velocity is first going up, then it keeps going up. So over here also the velocity is getting pulled up. Here, since the exhaust is there, so again the flow is upward. And everything over here, since the AC is there in this zone, it's hitting in this area or in this volume. So that is why the flow is all downward. So you can check this also. In this way, you can check how your flow is happening. So you can do this actually for the whole domain. Now, since I've applied it on the slice itself, so that's why it's only going to show me on the slice what is happening. But for your entire domain, also you can do that if you have 3D geometry. So for flows in which you have, so say you're doing a cyclic mixer or something like that, you can check whether your flow is happening properly or not. So this is one way to just check all of these values, whether your air residence time is proper, if you're getting the contours correctly, and if you want, you can post-process this as well. Okay. Switch this back to 150. Yeah. So coming back to the PPT. So now you have seen how to run the simulation. Now this is where the machine learning part comes into play. So if you have enough data, you can always run a machine learning code, because the machine learning is based or a machine learns based on the data that you provided. So more amount of data will equal to better results. So that is the simplest form of machine learning. So there are three main parts of machine learning that make the backbone of it. One is the data that is there. So that is the information that you can get from real world data sheets. In this case, you have the CFD data. And then you have the mathematics and the statistics. So this is where your linear algebra, calculus, probability, statistics, all of these things that govern all the mathematical problems are there. So whatever data you get, ML is just running all of those mathematical equations and formulas. And lastly, you have algorithms. So these are codes that you have set up to just run it iteratively one after another, similar to OpenFOAM. OpenFOAM is also based on algorithms. So you have the piezo algorithm, you have the pimple algorithm, you also have the simple algorithm. So those are just mathematics running one after another again and again. So within algorithms for ML, you have neural networks. So these can, and you also have something known as supervised and unsupervised learning. You also have something known as okay, let's leave that. So you have supervised and unsupervised learning. So these are again based on the models that you specify. Neural networks are depending on how what you want to solve using the ML code. Okay, so talking about neural networks, these are some of them. There are also more, so just keep that in mind. Okay, so the very first one you have is an artificial neural network. This is by far the simplest one, and it isn't that accurate, but for the application that we are trying to run, it's fairly decent. So this one is inspired by the human brain. So it perceives data just the way that we do. So if you see something, like from school you're taught that 1 plus 1 is equals to 2. So this is what the model does, or the neural network does. It, if you teach it that 1 plus 1 is equals to 2, 2 plus 2 is equals to 4, and then you ask what would 3 plus 3 be, by default it should say 6, but it may happen that it may say 5 or 7 or something like that. So depending on how much data, now in this case you have just given two times the data, so you only have given for 1 plus 1 and 2 plus 2, so that is why it does not know what will 3 plus 3 be. It might give you a wrong answer. So that is what this neural network does. So if you have more data, it will give you an accurate result. If you have less data, it will, your accuracy will start to vary. The second one that you have is the convolutional neural network. This one is usually used for processing your visual data. So if you have images, videos, and you want to process that, that is what this is the neural network that you can use. Then you have recurrent neural network. So this is again using sequential data. So if you have time data, or you have some time series data, and you also have natural language processing, so you can use this particular neural network. And lastly, you have the most famous one for CFD, at least, is PIN. So PIN is your physics neural network. So this is a little bit more advanced when compared to artificial neural network. This one uses your ordinary differential equations and partial differential equations. So what this does is, you, in CFD at least, we have two case studies present in our repository based on just pins. So you can train a model or a neural network with physical CFD data that you have. So you will have to run, in this case, you have to run quite a lot of CFD simulations to get an accurate result. But what it does is, it uses the physical sense. So whatever parameters you set, it will try to analyze it based on the physics that you are solving and the equations that you're solving. So if you're solving Navier-Stokes equation, it will use that. Along with that, the physical properties of it, and whatever input parameters you give, it will also base all of the results on these values. So it takes a lot of time, and it's fairly accurate as well. So for now, we have tested it for steady state flows, and in the future, we're also going to test it for transient flows. So let's check that as well. So for this case, we have only run ANN, that is artificial neural network, because that's simple and it runs quickly. Okay. And coming to the next part of the algorithm part, there are also learning models. So your learning models vary. These are the four commonly used ones. So you have linear regression. So this will predict your continuous numerical values. So this is the model that we will be using in the ML code that you have for this particular case. There is also decision tree. This one splits data into branches, and it will reach a prediction based on that. Then you also have a random forest. This will combine multiple data from these decision trees, and it will help you improve the accuracy. And there's also something known as overfitting, underfitting. So those are how accurate your results are going to be based on your input, output. So there are additional things. They're also known as something known as weights. So we'll check that in a bit. And lastly, you have deep Q networks. This one combines both your reinforcement learning with deep neural networks. So these are the pinnacle of neural networks, you can say, or learning models, because they use real world data. They take time as well, but they are accurate enough. So these are what are used in your autonomous vehicles and data processing, whatever you require. So ChatGPT and all of those things use something like this. So you have enough data, you train it on that. You have neural networks as well that are fairly complex. They're quite large models as well. And based on that, then it gives you fairly accurate results based on all the data that it has. So speaking about artificial neural network, there are some things that you have to understand before we see the code. So something is, so you have three main layers in a neural network. One is your input layer, second one is your hidden layer, and third one is your output layer. So the input layer is where you will give all of your input parameters. Now in this case, our input parameter is going to be the X, Y, or Z coordinates of your exhaust. Now, since I said that we are varying the distance of the exhaust, so the coordinate of that exhaust is going to be your input layer. The hidden layer is going to consist of all the neural networks that you're using. So you have the neural network, you also have the model. So in this case, we're using the regression model. And it will again based on the hidden layers, on how many hidden layers you have, your accuracy will depend on that. So in our case, we have used 6 hidden layers, and they all are connected with something known as a neuron. So those are around 256 neurons. So you have 6 hidden layers, 256 neurons. Based off of this, it will go back and forth. It will see the input data. It will try to compute the output based on that input data and the data that we have provided. So this hidden network, or the hidden layer, what it does is, whatever data we're providing, the training data, it will study that, it will look at it. So based on the values that you set, so in this case we have 256 data sets, and within that you want to check it around 500 times every time. So the hidden layer itself will have something known as a weight. So a weight is just your feedback. So you will have something known as a positive feedback, negative feedback, similar to that. So if your input layer is giving you additional terms, or it's trying to improve the data, so that may happen at some point. So that is when you have a negative feedback. So you will have a negative weight in simple terms. Whereas if your output is accurate, and you want to reduce on the time or something like that, you can also add, that is known as a positive weight. So based on how good your results are coming, you can change these weights to save time or to increase accuracy. There is also zero weight. You can add zero weights as well. So again, that is defined by, you can either define that, or you can let the neural network do it by themselves. And lastly, you have the output layer. In this case, the output is the air residence time. So we given the X and Y, X, Y, or Z coordinate system of the exhaust, we let the neural network calculate that, and at the end it will give us the accuracy or the output of the air residence time. So we've done this for training. We've also tested the data, and then we've got the output as whatever values you have for 4 values, and then you've seen the accuracy of it. So the accuracy will be calculated in percentage. So this was everything about the neural network that I said. You have 6 hidden layers, 256 neurons, 80% of the data is set for training, 20 is for testing. And for this particular case, we had ran 24 CFD simulations and the regression model that it is using. Now, in the code or in the file, if you go, you will have 3 files, right, in the drive. So one of that is the ML code. So in this one, the code is for at a distance of 1.3 meters and a distance of 1.6. So you have 24 simulations for each of these, okay? Each of these distances. So for at a distance of 1.3 meters, you have 24 simulations. At a distance of 1.6, you have those 24 simulations. So again, this is just uh, the slice wherever you're taking at either a distance of 1.6 or 1.3. So this, I'll show you for 1.6. So let's see the training data. So you can open this in Excel. It's just have the X, Y, Z coordinate system. So in this case, X and Z. So this is the distance or the position of your exhaust. And this is the air residence time that we wanted to train on. So so what we're saying is that at the coordinate system of X and Z, when your exhaust is at this particular position, your air residence time at 1.6 meters was around 903. At this particular distance, it was this value. So this is what we're training it on. Okay. And then you also have a testing data. So this is the value. So we have around 5 values for this. So at this particular location, the air residence time was this, and this is the predicted value that we've got from the model. So you can see that it's not very accurate, but it's close to that. You have 732, here it is 815, you had 1200, here it's 1046. So again, the accuracy may vary based on how much data you have. So the more amount of data, the more accurate your solution will be. Okay, so I'll show you the code as well. So to run the code, you can run it two ways. So one is you can run it locally on your system. So if you have Python or you have all the libraries in place, you can run it in VS Code as well. But since I don't have all of those files, I will run it on Google. Okay, so this is my Google tab. So say I open a new Google tab, you can use Google Colab. So Google Colab Python or Google Colab, you can just type that and click Google. It will ask you to sign in the beginning. So in my case, I've already done that. And over here, you can upload a new file. So in this case, you can just upload the file that you have over here. So it's saved under Ubuntu, home, and OpenFOAM. So 9 and ventilation tutorial. This is my ML code. So I will open the 1.6 ML code. So this is your file. So you can open this file and load it. So let's wait for this to load. So depending on the internet speed, it may take some time, it may take less time. Yeah. So is the code visible or should I increase the font size?
Little bit in it.
Little bit, okay. Now?
Fine.
Okay. Yeah. So this is one thing that you have. This is your code itself. The second thing that you have to import. Now, as I showed you, we have this training and testing data that we have to let the code know. So over here, we load that. So in Google Colab, you can scroll down or you can click the left side icon that looks like a file or folder. You can click that and let this load for some time. Yeah. So once this loads, you can upload your .csv files that were there. So in this case, I have this .csv file for training and testing because both of these files will require. So it will give you a prompt that kindly save the data, because once you close this tab, it will delete everything. It does not save anything. Okay, so make sure that if you're running this particular ML code, make sure that the file is in .csv, because it happens that when you open the file in Windows, it may try to overwrite it as an XLX, as an Excel file plugin. So just check that. Okay, so make sure it's in .csv, or you can change the value over here. So this is the files. So we've loaded out the files that we have, the .csv file, and then we have the actual code. Okay, so I'll close this tab, otherwise you won't be able to see the entire code. Okay, so now in this code, you have some libraries that you have to import first. So we are importing the NumPy library, that is for your mathematical operations. Then you're also including the pandas library. So that is for reading all your tabular data, because we are using the CSV file. Then you also have some of the functions that you will be using. So these, so again, this one is to split the data into different types. So you have 80% training, 20% testing. So those things can be done using this function. You also have some functions to calculate the accuracy, mean absolute error, mean squared error. So all those things are there. Then you also have a library for importing the neural network. So in this case, sequential. So this will create a neural network for you. It will create an empty neural network. Based on that, then you can put in the parameters. And there's also a supporting part. So sequence and dense will go together. So your dense is, it will connect all your neural network. Okay, so how many neurons you want. So that is done by dense. Whereas sequential will just create the neural network, an empty neural network. So based off of dense, or the values that you put in dense, it will give you that you have six hidden layers, or you have 10 hidden layers, or you just have 2 hidden layers. So I'll show you how that is also there. And then your regression is your model. And then you have min-max scalar, that is to scale your data between 0 and 1. So if you have data like 100, 200, 300, we'll scale it down to 0, 0.1, 0.5, and the maximum value will be 1. So that is something that is used by the code itself. That's why we've imported all of those things. Now, the very first thing you will do is load your training data. So this line is doing that exactly. So it is loading this air residence time and the train. Okay, so 1.6 train.csv file, and the skip header one, if you saw in the file. So yeah, this is the one. So the very first line, it has this XZ residence time. So we're just letting it know that to skip that, otherwise it may throw an error. So it just has to take these values. Okay. Yeah. And then we are extracting. So we're telling that train on the X data. So the X data is at this particular location or position of that particular column. Y data is at this particular column. And then we are creating this X train test, all of these variables, because we're going to be using it later on. And yeah, then after that over here, as I said, your scalar part, you're scaling your data between 0 and 1. So whatever values are set under X, it will try to scale it between 0 and 1. So that is what it's doing over here, scalar fit and fit transform, and you're using X train. So X train, we've used it over here. And same goes for Y. You're going to train, same goes for Y as well. You want to scale it as on that. And then you also have X test. So this is your testing data that you have. And you're going to use the X test based on the Y trained data. Okay, so you're going to train your data and then you're going to test that. So that is what is happening in this particular case. Then over here, you define your model itself. So your neural network, you're going to be doing it here. So again, model sequential. So that is going to create an empty neural network. And these are, so how many times you type this depends on how many hidden layers you have. So in this case, we've typed dense 1, 2, 3, 4, 5, 6 times. So it is going to, it's going to first, it's going to execute the first line. So that is going to check the data set that you have. So 256 is your 256 data set or your neurons, and it's going to do this 6 times. Okay, and below that you also have how many times it will see the data and all of those things. So this is what will give you your neural network information. So you have a neural network, you have, if you've written it 6 times, that means you have 6 hidden layers, and then you have 256 neurons. That means 256 data set it will every time check. Another thing is about the model to compile. So your Adam, it will update the weights during training. So if it runs this first line and say during that time it had, at least your output was not that accurate. So it will try to add in some positive feedback to get that accuracy a little bit closer to the actual value. If in case it is overly accurate, then it will try to reduce it down. So that is what is happening in this optimizer. Loss is going to be calculated by the mean square error. That is what is going to happen. So that is why we've imported that particular file. Same goes for training the model again. Over here, this is the model fit. So the epochs over here is 500. So the epoch is how many times your model is going to see that training set. So in this case, it's going to see it 500 times. And at each time, it is going to see around 256 data sets. Okay, so your batch size is data set. And the verbose is just so that it runs properly. And lastly, then you have your R square, in this case, R2 score. So your R square is going to evaluate your regression quality, since we're using the regression model. So for the quality or the accuracy of that, it's going to compute that based on whatever values you get. Now over here, we're going to import the testing data because we want to test whether the trained data is accurate enough or not, or the model itself is accurate enough or not. So that is why we're importing this particular file. Again, this one will assign columns X, Z, residence time. Now you're using pandas over here to convert that data set so that it is readable, or to read that file that we have. And then towards the end, then we have all of the printing part. So you can print actual class, predicted class. So you'll see that when we run this code. And it will also print out your accuracy, mean square error, all of those things. Okay, so now once you have this code and you've imported those files, you can just do run all, or you can physically run one of them. So in the bottom, it will show this. So now it is going to read. So it has read this data 30 times, 40 times, 50 times. So again, that data set that we've provided is going to read it up to 500 times. Based off of that, it is every time it views that data, it is training the model. So the model knows that 1 plus 1 is equals to 2, 2 plus 2 is equals to 4. So that is what it's doing. Okay. So in this case, it's checking the XY coordinate, and then it will give you your residence time at the end. So you can scroll down. Yeah. So it's run around 300, 400. Yeah. So you can see that once it is done, it gives you a tick mark as well. So in the end, it will give you this particular thing. So actual class, so the data that we provided for testing was this. So the air residence time at a particular value or a particular position was this. Okay, for each of those, we have the value. And this is the predicted value that it got. So for around 732, it predicted it to be around 810. 1208, it predicted to be around 1018. So again, based on that, then it gives you an accuracy. So overall, the machine learning program is around 90% accurate. If you want to reduce this, if you want to increase this accuracy and reduce the number of error that you have, you can provide it more data. For more data, you'll have to run obviously some more simulations. But the overall use case of an ML code is, if you have enough set of data, so if I know that a flow or a cylinder at that particular distance will have up to this particular CL or CD value, if I have that data in place, I won't have to run the simulation again and again if I want to just vary, say, the distance or the position of it. So I can train a machine learning model for that. I can just give it an input value. So in this case, we have given it for position, say 300, 400, my cube itself. And if I want to check what will be the CLCD for that particular cylinder, it can do that as well. So again, there is a test case using the pins model for that. So this was for Reynolds number 10, 20, 30. So for that, the intern had created a proper pin model. He had done CFD data, and based off of that, he was predicting whether if you move this cylinder between 10 Reynolds number to 30 Reynolds number, what will the value be? So that is what a pins model does. And a pins model is far more accurate than an ANN, because obviously the ANN is just using the data that we provide, whereas the pin model is also solving the PDs and ODs that we provide. So again, that's farly more accurate.
Ivan, sorry for interruption.
Yes,
Can we just take a break and request the participants to fill the attendance form?
yes, ma'am.
Okay. So, participants, we have just posted the attendance. Please take a while and please mark yourselves present. We are waiting for a minute. I think we are done. Now we can proceed with the lecture. We have also put it in the YouTube just now. Okay, so the people who are watching through YouTube can also take a break after a while and mark themselves present and then continue watching the demonstration. Okay, man. So now we can continue.
Yes, ma'am. Yeah. So now whatever I've shown was just demonstration part. Now, if you want to try this particular case, just the ventilation or the CFD case, there is the ventilation case file. So you can open that and you can see the template one. You'll have the ventilation template file. So under this, you have 3 of these files. Okay. So now if you want, you can do it with me, or you can just watch and you can then later on see the video itself. So if you're doing it with me on OpenFOAM 9, these are the commands that you can run. So first you go into your velocity folder and open it in the terminal, or you can directly go through your terminal itself. So say, okay, I'll just close this one. I'll open a new terminal. So say you are opening Ubuntu freshly. Okay, sorry, I opened the wrong one. Ubuntu 22. Yeah. Okay, so say you open your Ubuntu for the very first time, and then I will open OpenFOAM 9. So I'll source it OF9, and I can type run since I've copied it to my run directory. Okay, so I can type OF9 run. So once you're in your run directory, now you might only have 2 or 3 files if you're starting off new. I have too many files for now, so I'll just go into the folder that I have. So to enter any folder, you can do cd ventilation tab, and I want to enter ventilation case. I want to enter ventilation template. Okay, so now I am in my ventilation case. Okay, so you should have something like this. Okay, so you'll have 3 folders. Now from these 3 folders, you first have to solve for velocity. So I will enter the velocity folder, and once you enter the velocity folder, you'll have to do block mesh, topo set, create patch field, and lastly then you'll have to do the solver, that is simple foam. Okay, so now this is a very simple case, so it will run quickly. So first what we do is clear this so it's visible for everyone. Okay, now you're in your velocity folder. Okay, so first thing you will do is block mesh. Okay, so has everyone, if anyone is doing it with me, has anyone done this so far? Block mesh. In the chat, just type a yes, it's fine. The file is available on the drive. Yeah. Okay. Okay, fine. So once you've done block mesh, I'll show you the mesh. You don't have to do this, it's fine. Touch foam.foam. You can directly open Paraview as well, but mine it does not open because the RAM gets too full. So that's why I'm using the touch foam.foam command. So just open this. Ventilation case. Yeah. Okay, so now if you see, it's just a cube, and this is width to this. Okay, so it's just a simple cube. Okay, there's nothing more. Now to create the door, the AC, and the exhaust, we will be using topo set. Okay, so I won't explain what exactly is topo set and all. We've done that in the previous session. So to just simply type in topo set. If you want, you can open the file. The file is in your system folder. But now since we don't have that much time, I'll not go too much into that. So you can just type topo set. Okay, you just type this. Is the command visible? Yeah. So once you do topo set, it should run fine. It should show that it is creating phase set, phase zone. Same goes for, it will create C1, C2, C3. Those are the names that I've given. So now if I open it in Paraview, I'll just reload this file. Now if I go to load read zones, and I switch to Okay, I'll just lower the opacity. Okay, sometimes it shows, sometimes it doesn't. Yeah, okay. So this is the door using Toposet. Now we've created a face named inlet. Then we've created a face named AC, and we've created a face named outlet over here. Okay, you can see it with the mesh as well. So it's very, very coarse. Okay, it's just to help you run the simulation quickly, and you can have a feel of what exactly you have to do to run this particular simulation. Okay, so has everyone done till here? Done Toposet? Okay. Now, once you've done Toposet, now when you're creating a face in OpenFOAM, now OpenFOAM itself does not know that I want to apply a boundary condition on that face. I've done block mesh, I've done Toposet. It views it as a zone, but I haven't assigned it as a patch. Okay, to convert a zone to a patch, there's another file named create patch. Okay, now create patch, it's actually create patch dict. So that what it does is you can assign phase zones to be converted into a patch. I'll show you this just briefly. I'll show you, you don't have to open it on your own. Create patch dict, this is the file. So what we are doing is we are creating a patch named inlet type patch, and from where are we getting it? We are using construction from set, and the patch that it is going to set is from set in. So if you open the topo set, and you will see that my face zone that I've created is named as in, whereas for outlet it was out. So those things only, it is accessing all the data from topo set, and it is plugging it into create patch, and it is creating a patch. Okay, now to keep in mind, when you're doing create patch, you want to overwrite a file that is already present in OpenFOAM. Okay, so in this case, you want to overwrite the polymesh folder that is created by blockmesh. So for that, if you just type create patch, it will create a file named one. Okay, so now if you see, there's only 0 constant system. But if I just do create patch, it has created the patches, but see where it has created. It has created a polymesh separately from the block mesh. So now if I copy this polymesh into block mesh, it will throw an error, like copy it into constant. So this is the polymesh that has been created by block mesh. So if I try to just paste it over here, it will throw errors saying that it does not know what is going on over here. So to avoid this, let's delete this. The create patch field, it has, you have to type at the end overwrite. Okay, so what this overwrite will do is the pre-existing polymesh that has been created by blockmesh, it will overwrite all of the data. So you will have the physical points, cells, all of that that has been created by blockmesh, but the topo set or the patch data that is being newly added, it will add it to that existing file. So now if I do create patch, and if I see the file, it has not created any additional file. But if I go into my constant and polymesh, and if I open the boundary over here, or if I check any of the other zones, it will show that it has created my inlet, outlet, and everything. So I'll show you how does that look in Paraview. Okay, so now if I load my file, before loading, I'll scroll on top. So see now over here, you only have group wall, and then you have internal mesh, patch wall. So these are the only 3 that are there. But now if I reload it, see now it's showing patch AC, inlet, outlet, patch wall. Okay, so these are all now created. Now I can add a boundary condition on this. Okay, so this can be done. Okay, so now you have created that. So has everyone done it, done till here? Create patch. Okay, create patch dash overwrite. Okay, has everyone done this? Okay, okay, fine. So once you are done creating your patch, now you can run your simulation because I've already set the boundary conditions for it. So under U, all the boundary conditions are set. So you can directly run it. So you can either run it again in a single core, simple foam, or you can run it under decomposed condition. So decompose, par, enter. So now I've decomposed my case. You can see that it will have more files. Yeah. And once you have decomposed it, you can do mpi run dash np for simple form and then parallel. Okay. So now the simple form, while it is running in the chat also, I will type in the command. If you want to run it for decomposed version, decompose par, and then you type mpi run dash np for simple form dash parallel. Okay. So this is the command. So while this is running, you can also do another thing, that is to compile your solver side by side. So you can, if you're on WSL, you can just right click this and you can duplicate a tab. You can right click and duplicate, or you can open a new tab as well. It's your preference. Okay. Now in this case, I have duplicated it. I'll do this to WSL. Okay, so it has opened it in my other directory. I don't want to go into that directory. So I'll do it the physical way. So what I can do is, while the simulation is running, okay, for velocity, I can enter my ART form. Okay, go to the ART form, not air RT. ART form, where the .c file and the create fields file is there. Okay, and you can right click and open in terminal. If you don't have this option, you can go the long way. You can again open a new terminal, source your OpenFOAM version, do all of that, or you can wait for the simulation to run. Okay, once the simulation is done, you can do cd dot dot get out of this folder and then enter the ART form part. Okay, so what you have to do now, if you are doing it either ways, you have to enter the ART form file. Okay, so I'll just source again my OpenFOAM 9. Okay, I'm already in OpenFOAM 9 then. Right. Okay, let's try it once more. I have to first go to WSL. OF9. Yeah. Okay. Now, while your simulation is running for velocity, you can compile your solver using wclean. Okay. So wclean. Okay, there is no wclean. I have to first enter that folder, cd art foam. Okay. So now I'm into my art foam file. So now over here, I can do wclean to just clean any file that was previously there, or I must have compiled it and must have not compiled properly. So those files can be deleted off by using the wclean. And then you have the wmake. Okay, so now your wmake, it will run the command for compiling all your C file, header files, everything that is required for air residence time. Okay, so you can do this while the simulation is running. The other simulation should be done by now. We are at iteration number 3000. Okay, so I'll type in the command for compiling as well, wclean wmake. In case you are not able to run this right now, the command is in the PPT as well, so you can refer to that as well. There are also steps in case you want to compile a new solver, or you want to see how is this particular solver compiled. Those steps are also there in the PPT. You can refer to that. Okay. So once the simulation is done, we have to copy the U file from the last time step into the scalar file or the air residence time file folder. Okay. So wclean, wmake, that is done. Let's see the other terminal. Yeah. So my solver is compiled. Okay. So I can close this terminal. I can keep it open if you want. So once this is done, we'll just use this terminal. Okay. So I'll close this one. Which iteration? Around 4000 we've reached. 4100. Okay. So is anyone trying to compile the solver and run the simulation? People who are trying, just raise your hand or put a thumbs up or something like that. Okay, okay, great. Okay, so this is almost done. Yeah, 5,000. Yeah, done. Okay, so now if I go to the velocity file again and I refresh, so if you open any of these processor files, everything is within this processor. Okay, so now I want to reconstruct my file. Okay, so now I've distributed the file, I ran it, and I assigned each of the work on one of my processor. Now I have to collect that data. So for that, you type reconstruct par. Okay, so to decompose, it is decompose par. To reconstruct, it is reconstruct par. Okay, so when you type reconstruct par, all the files that are there in each of the processors, it will start writing that. I'll type in this also command in the chat. Reconstruct par. Okay, so reconstruct par will reconstruct all of your values or all of your data. Then again, you can open this. Yep. So now if you refresh, so you have all of these files are outside. Now out of this, we only require this last time step file, 5,000. Okay, so is everyone able to get this file so far? I'll wait for all of you. Screen is not visible. Paris, can you confirm if my screen is visible?
It's visible.
Okay, okay, fine. Okay. Yeah.
It's
Okay,
visible.
okay, fine. Yeah. So is everyone able to reach up to this step? Completing the velocity and compiling your solver. Once you run your simulation, you have to reconstruct it to see all these files. So the command is in the chat in case you missed it. Okay, okay, good. Now for velocity, you can enter, yeah. So you can enter time step 5,000, and from here you have to copy this U file that is there. Okay, just the velocity file. So copy velocity and paste it into, go back out, go to your velocity template and paste it into AR, this air RT in the 0 folder. Okay, delete the zone identifier if you have to. Okay, so I'll again repeat this. In your velocity file or in the velocity folder, scroll down to the 5,000th time step, open that, and from here the velocity file that is there, you copy this into your air RT folder under this 0, under this over here. Okay, so you will have now in your air RT file the scalar, that is S, or the residence time term, and you will have your velocity. So this is your initialized velocity. Okay, is everyone able to do this so far? Copy pasting the velocity file into the air residence time file folder. Okay.
Yes.
Okay, good. Yeah. So now you have to now enter the air RT folder. Okay. So you can do cd dot dot. If you're in your velocity file, you can do this in your velocity folder. So now I'm again back outside my folder. Now I can enter cd air RT form, air RT file. Okay. So now I am in my air RT folder. Okay. So if you want, again, in this case, instead of running again block mesh, toposet, create a patch and all of those things, if you don't want to do that every single time, you can use the all run script that is there. So to run the all run script, it is bash / all run. Okay, so you can either use bash, you can also just use dot all run, dot / all run, so that also works fine. Okay, and in case it gives you an error, so in this case it gave me an error over here. Okay, it just launched ParaView. Yeah, so in case it gives you an error like mine did, you can always open. Okay, the ART file of mine does not have an all run file. Okay. Okay, 1 minute. I'll just cross check in which folder this. Yeah, it has here one. Okay. Okay, so in case it gives you an error, you can always do it the manual way. So I'll just clean the case. Foam clean tutorials. It's clear. Okay, so foam clean tutorials. So again, first you do block mesh. Once you do block mesh, then you do toposet to define the face zone. Toposet. Once you do toposet, then you do create patch overwrite. Okay, so this part I've just sped it up a bit because we've already done this in the previous folder. So it's the exact same thing. Okay, so once you're done till here, can you just raise your hand, say yes, or just put a thumbs up? Okay, yeah, so you've done your meshing. Now you have to just run the simulation. Again, for this, you can decompose the case and then you can run the command mpi run -np number of processor 4. Then instead of simple foam this time, now you will type ART foam and then you will run it parallel. Okay. So the same command that you ran for simple foam, just change simple foam to ART foam. Now this particular simulation will take a good 5 to 10 minutes to run. So again, I have the simulation run so I can show you the results. The results aren't that accurate when compared to the previous case, but again, it does its job. If you want to just learn or to just run this case, now you know the process. It's a two-step process. So first you have to solve for velocity, side by side compile your solver. Along with that, then copy this file into ART in the ART folder, and then run the ART foam. So again, you see that it has many steps. So that is why I gave you the hands-on part so that you know how to run this case. So once you are done running the simulation, you can always view it in ParaView as it is. In the afternoon, I'll show you how to take a slice, how to take a clip. Yeah. Can you also please send? Yeah, so the ML case is also there in the drive link. So I'll show you that. Wait. Yeah. So in the drive, you have 3 folders. Okay. So one is your template file. You also have the ML code, and you also have this room, this MFHT room template. So this file is also there. So if you want to run this particular file, you can run that as well. And along with that, I also attached the Panjan's report. So if you're interested in understanding what is happening in this particular case, like the physics behind it and the boundary conditions in detail, you can check this report of his. He's mentioned everything. He's also mentioned the amount of simulations that they've done. So if you scroll down towards the end, yeah, so the results that they have, so you can see they've done so many simulations and then they fed all of this data. Now they've not used all of the data over here, just a fraction of it, but you can see the amount of simulations it requires to just train one model. So again, training a model isn't that simple, and just because everyone is doing it, that doesn't mean that you should also be doing it. Eventually machine learning and artificial intelligence will catch up in CFD, but for now, knowing what you're doing in CFD is much more important. And after you completely understand what you're doing and what inputs you're putting, only then try to replicate something and go for something as advanced as machine learning. Okay, so again, if you're interested in learning machine learning and all that, it's there on the internet. You have, like, now I've just given you a brief overview of what exactly is machine learning, what are the models, what are the neural networks. So there are in-depth videos on that as well. And if you are interested in pins model or in artificial neural network, so there are 2 or 3 cases on just the artificial neural network for this particular case. So the case that you're seeing over here, there are also 2 cases available on pin model. So those are also available. So once the website is back online, and I think towards today in the evening, Payal ma'am or Paris will show you an older version. We have a website, but it's the older version of the website, so it isn't that glamorous. But if you want to download files and you want to just see how it is, you can always check that. So towards the end of today, we'll show you that. So don't worry about that. Okay. So now while your simulation is running, once it is done, you can check it in ParaView. In ParaView, I'll show you in the afternoon all the post-processing things that you need to know. So I'll show you how to do, how to plot contours, how to calculate values of it. So if you want to calculate CLCD, you can do that. If you want to, now in this case, the CHD, the case that you just saw, the ART foam, how to plot the streamlines for that, how to take a clip, slice, and if you want to again post process some more data, if there's time, then we can always have a Q&A session on what you want to try and how can you do that in ParaView. Yeah. So is ART compatible on OpenFOAM ESI 22? So there are two versions over here. Now this particular one, the template file that I've shared you, it is for OpenFOAM. Wait, I'll show you that. Yeah, so these two files, they are actually using ART foam only. So I've modified the older case was just for OpenFOAM 9, just for OpenFOAM 9. So for this particular FDP, we thought of updating it to 2412. So we've done that. It's successfully running. I can show you for 2412 as well. So I've actually run this for 2412. So instead of OpenFOAM 9, I'll go to my run directory for 2412. So I had created for both because I know that some people over here are just running the ESI versions. Maybe that you might have some problems in the ORG version. So that's why the ESI version, for that specifically, we have created the 2412. So that should work on 22 as well, because there's close to no difference in terms of the version for 22, 23, and 24. At least for 21, there are a little bit changes, but nothing that drastic. So it should run fine. Okay. So you can try it. If in case you get an error for 22 version, let us know, email us, so that when we are aware that it does not work for that version, so we can update it maybe for that particular version. So that way, then a custom solver can be used on any of the versions. For now, this particular one will work properly for OpenFOAM 9, for OpenFOAM 2412. It won't work for OpenFOAM 12, because I tried running it for OpenFOAM 12. It gave me a lot of errors when I was updating it. So that is why I did not update it for 12. But for the other two versions, it will run fine. CFD AI and ML training program. So towards the end of this year, maybe in the advanced workshops, we will try to cover that. Because there's a lot of demand for AI, ML, and CFD coupling together. So that may be in the future that we might have something in that. Yeah, so Paris has also answered. So for now, as I said, that we have just two cases that are done on ML or PINS model, and most of them are very basic ones on artificial neural networks. So those are just the base of ML. So again, in CFD, doing complex simulations and making an ML model for that, it becomes very complex. That is why if you see even papers published on that, there are very few for complex simulation. Most of them are restricted to just laminar flow or just steady state flow. They aren't touching turbulent that much. And even if they're touching turbulent, they are not introducing too many models into it. So it becomes really complex when you have so many things going on. Yeah. Okay. Thank you, Mr. Vinod. Yeah. So does anyone have any other questions regarding the simulation or previous sessions? We can take that, or we can take it in the afternoon also, because we've already crossed the time limit. It's almost 1:16. So I think we can take that in the afternoon or in the evening at around 5 o'clock. We have a dedicated Q&A for that. So you can ask us during that time. Yeah. So I think, you have our email IDs. So for now, we can break for lunch. We can then come back at around 2:15. So that way, yeah.
Yeah, fine. So 2:15, Professor Tushar Chaurashi will join with us for the next lecture session. And then again, we'll have another demonstration session. And then the concluding session will be very important today, because I'll talk about how can you join with us, how can you contribute to the FOSSEE project and take yourselves forward in the learning process of OpenFOAM, and also not only enrich yourselves but enrich your institutes and your students. Okay, so please be with us till the end of the session, and Professor Prabhu Ramachandran will also be joining towards the end, and he'll be interacting with all of you. Okay, so yeah, I think all of you have marked yourselves present in the attendance form. If not, I'll just paste it once again. Okay, so now we can take a break and come back at 2:15. It's almost 1:20, Evan. So should we start the next session around 2:20?
Yes, ma'am, it works.
Okay, fine. So fine. So next, I'll inform Professor Tushar likewise. Okay,
Okay.
so please log in around 2 p.m. So that we all can be in the Google Meet on time. Okay, so thank you and bye bye everybody. See you in the second half.
are implemented, then some verification and validation test cases study, and then comparative result what we obtain, and what we finally conclude out of it, and then the publication of the student, and that's how the slides are arranged. So first, when we talk about the assessment of incompressible flow over any body, for example, the body shape can be either streamlined or bluff. So as an aerospace engineer, we often are interested in the streamlined body because it doesn't hinder the streamlines and it is aerodynamically more efficient. So as it offers less drag as compared to the blunt body. So and the blunt body on the other hand, it has high drag due to so much due to vortices which is getting created at the back. This creates a pressure difference and large eddies get created. So drag, which is actually the sum of skin friction and pressure drag, in case of blunt body the pressure drag becomes very high, so overall this the drag increases. But in the case of streamlined body, the pressure drag is very low, and we have only skin friction drag. So then another thing which we often see with the bluff body is the flow separation point. These are the main culprits behind the pressure variations which are there over if we are comparing a flow over these bodies. So let's take an example of incompressible flow over a circular cylinder. So if I take a cross section, I can see a circle only. So in this case, we have a circle which is a blunt body, and when we try to increase the Reynolds number, what we observe that the CD, if you see the comparison of CD plot, we will observe that the CD decreases or up to certain limit of Reynolds number. Thereafter it remains constant, and then again it decreases and then increases. So this region decrease and again decrease and increase is the region of turbulence, where we often get this peculiar feature. But the regime where we will see the uh, CD becoming almost near constant, this is the transition region. And the regime which I am going to discuss today is the low Reynolds number regime. So because we were interested to compare the existing result and see how the open form actually performs and calculate by validating with the whatever work people have done. So if the Reynolds number is low, the streamline doesn't separate. For example, if my Reynolds number is less than 5, then the flow is almost attached. But as I'm going beyond 10 to 40, there will be vortices generation and flow separation starts from the maximum thickness points. So flows, the streamlines gets separated from the body. And as again, if we are increasing Reynolds number beyond 40 or more than 40, then we observe the oscillating behavior of vortices in the downstream. So then if I keep on increasing beyond 150, the oscillation becomes unsteady. So we get unsteady vortices, and then we transcend into turbulence region. Now why this phenomena occurs? Because in case of low Reynolds number, we have the viscous component dominant. As we are increasing the Reynolds number, the inertia components try to become dominant, and that's the reason the CD drop will be observed. So the application of these flows, as an aerospace engineer, we um, often require these types of blunt body for some application related to re-entry vehicles. Because if we have the sharp edges or a sharp body, we will have high heat getting generated at those sharp nose points. So in order to avoid that, we need blunt bodies, and that's the reason as these blunt shapes find its application in re-entry vehicles, then missile, where we play with the nose of the missile. We try to make it slightly blunt to reduce the heat dissipation onto the object. And in the case of mechanical engineering, we have application in the, for example, if you see the this wind engineering, the bridges. So the bridges do oscillate when Reynolds number is very high. So due to unsteady vortices getting generated, this are very dangerous. So in order to properly design or overcome certain shapes of bridge, this it has find its application. Also in the case of the heavy vehicles, wherein the heavy vehicles have a blunt shape as compared to streamline, so they um, often reduce the pressure behind, which will increase the drag. So that's how we have to work as an application engineer in mechanical. We have to work on different shape to overcome these things. Now the equations are pretty simple if we are solving incompressible flow, because here the density is a constant. So we can put the density out of the uh, continuity, and also momentum we can separate out, and the term will be there in the pressure gradient and the viscous part. So the equations, particularly for momentum, for 2D problem in this case, is end up with x and y momentum equation for Newtonian fluids. And if we are working with low Reynolds number, then the other non-dimensional parameter which will be interested is CD and CL for the shapes. Now if we go beyond a certain range of Reynolds number that I have already shown earlier, so in that case, we need additionally the transport turbulence equation models. For that, our equation, which was very simple in earlier case, this equation, in addition to this equation, we will have the Reynolds stresses, and the whole equation will be time averaged. So that's the reason instead of solving Navier-Stokes, we'll be solving here Ryan's equation. So uh, and depending upon the Reynolds um, Rand's different order of turbulence model, we can solve this Reynolds stresses. Now, how the equations are discretized in OpenFOAM. So when we see this equation, here we are in momentum equation, we are trying to solve for velocities. So and the other term which is unknown to us at this moment is the pressure term, which is unknown to us. So in OpenFOAM, the equations are discretized. If I have to discretize the OpenFOAM equation, then there is a term called as H operator. Now what H operator does, so H operators, if I take the finite volume of the earlier partial differential equation, then H operator is the summation of the sources which are present in my Navier-Stokes equation, along with the neighboring nodes contribution coming into my particular momentum equation. So that H operator we calculate in OpenFOAM, and that H operator we put it on the right hand side along with the pressure, which is again onto the right hand side, and then we solve the momentum equation. So U momentum equation can be X direction and Y direction. Now, since we need an algorithm, because for incompressible flow, we don't have any pressure equation, so we need an algorithm. So in order to solve incompressible, the algorithms are the very famous algorithms are simple and piezo algorithm. In the case of simple algorithm, which is on the right hand side, you can see the flow chart of the simple algorithm. So here the pressure value is guessed in the beginning, and using the guessed value of pressure, we calculate the H operator term, which is HU over here. So we calculate the HU operator term, and then we update to get the velocity values, which is this. By updating uh, in this equation, I will get the velocity values as pressure was guessed, and this we have calculated. And so we will get the uh, cal- the calculated values of velocity, and this value again we put it in the pressure equation, which is the pressure Poisson equation. So in the pressure Poisson equation, we put all the calculated values so as to get the pressure value, or so as to calculate the pressure value. Now once we calculate the pressure value, we will put in the corrected velocity equation, and we will try to update and find the velocity value. This will continue. This process will continue. The loop will run again until we get the converged velocity value. This is the simple algorithm. So what we have observed here in the simple algorithm, we have a outer loop, because again after u we are going back and substituting to calculate this calculated velocity will become the guessed velocity, and the calculated pressure will again become the guessed pressure, and this keeps on iterating until we get the convergence for continuity and momentum. So this is simple is following the outer loop. Now if we are trying to compare the piezo algorithm, I have to use piezo algorithm. In the case of piezo algorithm, I won't be going to outer loop. Instead, I will be coming to inner loop. Now, what this outer and inner is, so since piezo is a unsteady solver, so here we introduced a time-based update. So depending upon the delta t or the corrector step which you have used, we will update the instead of going to up, we will update directly from the um, directly from next level, and we will be using the guessed pressure which was here, and then this step is as it is, but here over here using guessed pressure and the corrected loop of piezo, we will update the velocity. Okay. So when these two are combined, then we call it as a pimple algorithm. And so pimple algorithm, the advantage of pimple algorithm is that it combines both the advantage of piezo and simple. And because of that, what we get actually, because simple algorithm, we have freedom to relax the governing equation. So relaxation and advantage we get in pimple algorithm. Additionally, in piezo algorithm, we can solve the unsteady part. So with relaxation and unsteady part, instead of going for low Courant number, this pimple algorithm can even solve for higher Courant number. And you will see that even when your Courant number is going up beyond 1, still your OpenFOAM is able to converge with pimple algorithm. So with these algorithm, we try to assess the flow over a bluff body. In this case, we have taken a triangle. So a triangle was taken, and the far field were kept far apart so that um, so that the boundary effects of the no slip wall doesn't protrude into the far field condition. And then based on the Reynolds number, non-dimensional parameters, we set up the inlet velocity, and the viscosity we have taken of the reference. So we were trying to validate our work with the existing work. So here we try to compare all the algorithm, simple, ICO, and pimple and piso, and what we obtained that our result are in close agreement with the existing papers. And prior to that, we actually did the grid independent study, and the best mesh we have taken to calculate the results. So this work was for Reynolds number 20 because we have the paper reference paper for Reynolds number 20 with 0 degree angle of attack. So if you see here, then we increase the angle to 10 degree, and we also increase the Reynolds number to 40 because in 20, if you see, there are no such vortices getting generated at the back. So we wanted to capture that vortices, oscillatory vortices, and that's the reason we increased our angle to 40. And we observed the unsteady vortices generation and detachments. Then we compared the convergence of these solvers, and we observed that the simple algorithm converge fast, but the other algorithm like ICO, Pimple algorithm, the convergence, although we got the convergence, but it took more iteration, and the last one, the PISO, took the maximum number of iteration to converge, and the convergence also not as better as the other algorithms. So that's what we conclude by comparing different existing solvers of OpenFOAM. So as the simple is a steady state solver, so that's the reason it took very less time. But since being a steady state solver, it doesn't take into account the dynamic behavior of eddies, and that's the reason we should use other solvers. And now particularly the ICOFOAM and pimple foam solvers. So in the case of icofoam solver, it is using the solver libraries are particularly laminar case. So it is most suited for this type of runs. But if we want to increase the Reynolds number beyond 40 or more, then we should go for the pimple foam, because that will be more versatile to converge, and the unsteady nature will be preserved. Then the last solver PISO, what we observed that the CFL number we have to always keep less than 0.6, otherwise we were facing problem with the convergence because of the nature of the algorithm. So and while keeping that, our computation time actually increased, and since it's a turbulent solver, so it should be used for higher Reynolds number. So then we thought of increasing with the other student. We thought of increasing. So this is the work of other student. We thought of increasing the Reynolds number beyond and change the shapes. So if we are going for higher Reynolds number, we will be getting oscillating behavior of the eddies. Now, in order to study this properly, we need additional number, which is the Strohal number. So Strohal number calculate this oscillatory nature of the vortex getting generated, and we with this study we try to understand the Strohal number for these two cases, one with the blunt shape, another one with the elliptic shape, for Reynolds number 150. And we observed that at, as we keep the angle of attack to 0, for 0 degree angle of attack, the blunt shape Strohal number for both the cases, blunt and elliptic shape, are almost same, but um, then as we increase the angle of attack to 20 degree, again the values are almost close, but with the increase of angle of attack, the Strohal number is decreasing. This is due to the way structure getting uh, shapes getting different, and the flow separation points are also getting different. So that's the reason the Strohal number actually decreased as we are increasing the angle of attack. So then this was the work which students have published with the FOSSEE work. So I'm open to question. So if any. I'm open to any questions if you have. And the Strohal number calculation, I just want to brief. It's not there in the open form, but in FOSSEE we have shown how to implement Strohal number. So you can refer to the report of the student. So he has shown how to calculate the Strohal number in open form. Okay, so if any question, then ma'am, Payal ma'am.
Yes, yes, please. Hello.
Yes, ma'am. I think somebody asked, can you share the DOI of the articles? Yes, I can share it. If you Google me, if you will see in my Google Scholar all the papers. If any other question, then yeah. And just one more thing, we this work is not just stopped. We have extended it. We are going beyond. We are changing the fluids, and we are going beyond. And even we are trying to change the body. Instead of rigid body, we are going to different bodies. So that's how we are going ahead. And I am thankful to FOSSEE, the exceptionally talented student. They work hard for them.
Somebody has asked for the link of your Google profile.
Okay, okay. So just Google my name. I'll type Google my name on Google Scholar. I think, shall I wait, Palman? I'll wait for 2-3 minutes if no
Yes, yes.
question.
Paris, could you check if there are some questions in the YouTube link?
Yes, ma'am, I'm live on YouTube.
Okay.
Pranay is
Any question
answering.
there also?
Pranay is answering them. So,
Okay, great. So Mr. Datta has a question in the chat box.
Yeah, it's there. Viscoelastic problem case in OpenFOAM, it's there. The non-Newtonian, but that is non-Newtonian icoform. That is not using elastic part, but non-Newtonian fluid nature is there. If you want to particularly explore viscoelastic fluids, then there was a work, I think, done by uh, Fabro author in OpenFOAM, and even the founders, the founder of OpenFOAM. So that case studies, even the files and the solver setup are available with these two authors. So let me just Google and tell you. Favero. So this is their Giovanni Favero's work is available, and it comes with the new uh, OpenFOAM setup. If you are installing new version of OpenFOAM, this libraries are already there for viscoelastic. So which was first developed by this author, Giovanni Ferrero. So he was the first in OpenFOAM. So, okay.
I think there are no more questions, sir. So, yeah.
Okay, man. Then, yeah, thank you so much
Yes, yes. Thank
for
you so
your
much.
time. And I'm really sorry every time I have some time issue. Okay.
Okay, okay, no
Thank you, ma'am.
problem. Okay.
Yeah.
So,
Okay.
yeah, so Professor Tushar Chaudhary is one of our esteemed faculty partners from MIT University, Pune. So, if you have any further questions from him, you can write to us and then we can coordinate and get back to you. Okay, fine.
Okay. Thank
So,
you, ma'am.
thank you so much for joining, sir.
Yeah. Have
Thanks
a
a lot.
nice day. Thank
Yes,
you.
sir. Same to you. So, now we can proceed with the hands-on session, Evan.
Yes, ma'am. Yeah, I hope my screen is visible. I'll make it full screen
Yes.
and check.
Yes.
It's working, right? Yeah.
Yes. Yes.
Okay. So for the afternoon session on post processing, you can download the files from the drive again. It's uploaded over there. So under day 4, incompressible flows and post processing, there are two files over here. One is for OpenFOAM 9 and the other one is for OpenFOAM 2412. So again, depending on the version that you're using, you can choose either one of them. You can download both if you have both the versions. So for now, I will show you how to run a simple flow over a cylinder in OpenFOAM 2412, and then you can do the same thing in OpenFOAM 9 as well. The commands are exactly the same, and then we'll see how to post process data off of it. Okay, so I'll show you how to post process the coefficient of lift and drag using ParaView itself and also using a Python code. Yeah, so starting off. So again, once again, good afternoon, everyone. And now we'll be seeing the fluid flows and post-processing using ParaView in OpenFOAM. So this is the problem statement. So it's a simple flow over a cylinder, a circular cylinder. The diameter of the cylinder is 1 meter, and these are your domain dimensions. So this is the front view of it. The top and bottom will be symmetry boundary conditions. Left will be your inlet and right is your outlet. And the cylinder itself has a no slip boundary condition. And this is the fluid parameters. So you have a velocity of 1 meter per second, and your entire domain is going to be of around 40 meters. And the cylinder itself is at the origin. Okay. And another thing to uh, make note of, this is just a simple comparison between incompressible and compressible flows. So in OpenFOAM, I'll show you how to even search for a compressible flow case, because there were a few people who are interested in compressible flows. So I'll show you how to check those cases, and you can download them and run. Now this particular case that you can see is a tutorial case as well. So this is just a tutorial case from OpenFOAM 2412 using Sonic Foam. So key differences you will see that in incompressible flows you have a mathematically elliptical equation. So in this case you don't really require to specify a pressure at the inlet, whereas in a compressible case that would not be the case. You would have to specify a pressure inlet, and the pressure is linear in terms of incompressible flows, whereas for compressible it's non-linear. So what I mean by that is, you can see from the streamlines itself, right? So in compressible flows, before the fluid even interacts or touches the object, so the highlighter on, yeah. So before it even touches the object, you can see that there is already disturbances in the upstream flow. Whereas in a compressible flow, unless it is touching and the shock wave is created. Now over here, the place where you can see that there's a drastic change, there's a shock wave actually present over there. So unless it touches that shock wave, before that, all of the flow is streamlined and it's untouched. So those are some key differences between incompressible and compressible flows. Another thing is you have to take care of delta T, your mesh size and all when you're dealing with compressible flows. So those are some things you can take care of. And post processing, yeah. So first, let's see how to set up this case, the flow over a simple cylinder. So I hope all of you have downloaded the appropriate file from the drive. You can also download the PPT. It has some of the links that will be handy for you when you're doing post processing. But for now, you can download just the version that you have. So once you've downloaded it, extract it and copy it into your run directory. So I've already done that for OpenFOAM 2412. So again, if you don't know how to do that, you can copy it directly and you can then open it in your terminal. So now I'm using WSL. So let's zoom in. So first I type WSL. Yeah. And then I'll source my OpenFOAM version OF2412. Okay. In case you don't know where your run directory is, again, I will show you how to do that. So you can open your Ubuntu or terminal. So in this case, I'll just open Ubuntu 22. Now under this, first you will source your Ubuntu version, your OpenFOAM version. So 2412. If you have OpenFOAM 9, 10, 11, 12, you can copy it for that and you can run it. Again, for OpenFOAM 9, you can just type OF9 if you've created an alias. And once you've done that, you can just type run and it will take you to your run directory. And now in my run directory, it is under post processing. So I can just do cd post processing tutorial. Okay. So under this, I have all the files. Okay. So I'll just clear this. So now you are in your OpenFOAM directory in which we want to run it. Okay. So I'll open each of the files and I'll show you what is present within each of these files. Now it's a simple incompressible flow without any turbulence modeling or anything using SimpleFOAM. So we just have pressure and velocity. So let's open each of these. So I'll just briefly explain what we are putting for the boundary conditions. Again, this is all covered in the previous session, so I won't go too much in detail. So this is the velocity file. So over here, we're giving a uniform velocity of 1 in the x direction. So at the inlet, we have a uniform velocity of 1. In the internal field, we are adding 1 meter per second flow in the x direction. This is just to initialize the flow from the beginning. So your entire domain is initialized at 1 meter per second. If you want, you can set it to 0 as well. So it doesn't matter over here. So it's just that your simulation will start off a little bit more stable. Outlet, we have kept 0 gradient. That is, it will take the data from the closest cell or the last cell that is closest to the outlet and it will apply that. Top and bottom. So top, bottom are put into one particular boundary in a single boundary. So that is set to symmetry. You can also set it to slip. And if your domain itself is quite large, you can set it to 0 gradient as well. So where symmetry boundary condition is, it's in simple terms, it's an open domain. That is, we are not restricting your top and bottom to be as a wall. Whereas if you add a slip boundary condition, you're restricting it to be a closed domain. So your top and bottom will behave like a wall, but not a normal wall. It will allow the flow to just pass through it without causing any air resistance on the wall. The cylinder itself has a no slip boundary condition, meaning that it will behave as a proper wall. And the front and back are default faces. So those are set as empty. Okay, and same for pressure, we are setting all the boundary conditions to 0 gradient. And for SimpleFOAM, it requires one boundary condition or your outlet to be as a fixed value. Otherwise, the mass flow rate does not happen and it will ask you for P reference or P cell values. So to just avoid that, you can add the outlet as a fixed value for 0. Either way, pressure will be calculated during the whole simulation, so that's fine. Then we go to the constant folder. So under, now since we are in OpenFOAM 2412, you will see that the constant folder will have transport properties and it will have turbulence properties. Okay, so in OpenFOAM 9, these files are named differently, but they are same. So you have transport properties, but instead of turbulence properties, you'll have something known as momentum transport. So it's the same thing, momentum transport and turbulence properties. They both handle whether your simulation will be laminar or turbulent. You can tweak that. So I'll open these tools and show you. Yeah. So transport properties, you will set your kinematic viscosity over here. So you've seen that in your icofoam case. And your turbulence property over here, in this case, we're solving for laminar. If you open the morning case that I shared, the turbulent, the ART foam case. So in that, if you open the turbulence properties or the momentum transport in that particular folder, you'll see that we are using a turbulence model K epsilon. So within that, you specify over your RAS or RANS model. And within that, you specify the model that you're using, the turbulence model that you're using. So that can be seen in the previous files. So over here, you're solving for lamina. That's why it is set to lamina. If you ever want to change it, you can just backspace it, type RAS, and add the block also with it. It will ask you for which model you're solving and all of those things. Okay, so these were the two files in your constant, and then we have the actual mesh file, and I'll show you also the control dict file. Decompose par, FV scheme, the FV solution, they are all the same. Yeah, so the control dict solving for simple foam, start time 0, end time 5, delta t we've kept at 1 since it's a very coarse mesh, and we don't require too much we don't have too much time to just run the whole case. I just want to show you how to run this case, and then we focus on the post-processing part. So that is why we kept delta t at 1. Otherwise, you would have to calculate based on your CFL number and all of those things. So the delta t is set based on that. And if you scroll down towards the end, now in your control dict, you'll find something new. So till here, everyone is familiar that you have your solver name, start time, end time, and in the morning you also saw that how does this purge write work, and write format, ASCII, precision, and all of those things. Runtime modifiable will just allow you to change or make any changes to this file. So you can change your start time, end time when your simulation is running. So if you want to increase the duration of your simulation, you can change your end time while the simulation is still running. So that is what your runtime modifiable can do. If you're solving for piezo foam or pimple foam, especially in pimple foam, it will ask you to even specify your max current number. I'll show that as well. So if time permits, I will open one of the tutorial files and show you how what else changes are there in pimple foam when compared to simple foam. And another thing to note is now you have a functions tab. Okay, so now functions will have all of the post-processing functions that you want to calculate. So in this case, since I said that we are going to calculate for coefficient of lift and drag, you can either use a pre-existing function in OpenFOAM. So that will give you force, and it will give you force coefficients. And then you can write a custom Python script in OpenFOAM or in Python itself, and you can run it in OpenFOAM. Or you can open it in ParaView and post-process it over there. There is also a third option in which you can use the CSV file, or you can extract all of this data and open it in Excel and plot it in Excel if you want. So that is the last option. If you don't know Python, if you don't know ParaView, you can open those files in Excel and you can just put in all your formulas over there and solve and plot everything over there. So that is possible as well. But before you get that data, OpenFOAM needs to understand that you want to post-process something, or you want to extract some data out of your simulation. So that is where your functions tab comes into play. So within this functions block, you will add your different functions. In this case, we want to compute forces and we want to compute coefficient of forces. Okay, so under forces, the first thing you will see is the type. So in this case, now for OpenFOAM 2412, it is a little bit different. For OpenFOAM 9 also, it is a little bit different. So again, it might give me some errors over here. I'm not sure if it will work this way because the libraries are a little bit different when they are defined in another version. So let's see if it gives us any problem. We'll switch to OpenFOAM 9. It's not a problem. It will also prompt us that this library does not exist, or you have to give it in the proper way. So let's see that. Okay. So the very first thing is type. So type forces, function object library. So from where do you want to access this function object? So whatever formulas are there to compute this, it's all under this library. So under libforces.so. And then you have output control. So these are just whether you want to display it in the terminal and all of those things. So you can specify those things. Then you have patches. Now this is where you will add the patch which you want to compute over. So in this case, I have a patch cylinder. So over here it's cylinder 1. So I'll just check now whether in U we have cylinder. So we have cylinder, but we don't have cylinder 1. So I'll just clear this. So for those of you who are on OpenFOAM 2412, just make the change over here to change it at cylinder. I think it's a typo over there in forces. So when you're computing, you'll have to specify a patch over which you want to compute. In this case, we want to compute the forces over the cylinder wall. So that is why we specified the patch cylinder. Then you give some general values for rho. So in this case, it is rho infinite. And then your rho infinite or your value for rho is 1.225. So this is important because we'll be using it for post processing. You'll see why exactly. Then coef r, again, that's set to 0. Lift direction is in the y direction, drag in the x, pitch axis in z. So all of those things, you can leave this as default. If you want to change them, you can always change those. Then the next block that we have is your force coefficients. Okay. Okay, I have a question where the files using the calculate this force. Okay, I'll explain that. Wait for some time. Okay. So forces, then you have force coefficient. So again, the type is going to be force coefficient, and this is also under the libforces library. Output control, again, at time step, every time step it will log the data. If you want, you can set it up at different intervals as well. So if you want to log it after every 10 time steps or every 10 iterations, you can do that as well. If you want to log it after every 5, you can do that as well. And over your log, yes, that means that in your terminal, do you want it to display any of the data? So you can do that as well. If you don't want it to display in the terminal, you can switch it off. You can just type no. Again, patches, whatever patch you want to specify it on, in this case, cylinder. Output control, again, this is for the terminal part. And then you also have, again, the same things for rho infinite, and then the value for rho. So your density, and along with that you have coefficient r, lift, drag, pitch. So those are the same things. In addition to that, you will have something known as the magnitude of u infinite. So you'll have your free stream velocity. So that is the value that you set over here. So in our case, we have set the free stream velocity to be 1 meter per second. So we'll add 1 over here. So 1 meter per second, 1. Your reference length, so as I said that the diameter of the cylinder is 1 meter. So my reference length, that will be 1 meter. In case you change the diameter size, you can change this value as well. And lastly, you have your reference area. So now since we are solving a finite volume method, so there will always be some depth in your cylinder. You're not solving purely for a 2D case. It is slightly 3D, but it's only that in the Z direction, you're specifying one cell. So that depth is still there. So how do you compute that? Okay. So coming to the PPT. So this is the 3 ways you can do post-processing. In ParaView, you can write a Python code, or you can do it in Excel. And coming to the reference area. So now say we have this particular case, a cylinder. Okay. So if I were to give a reference area for it, it would be the surface area of the cylindrical part, leaving these 2 flat areas, because this is going to be a hollow cylinder. Okay, so if I want to add the area reference or reference area in the control dict, I will have to know the height of my cylinder, that is the depth in the Z direction, and the radius of my cylinder. So based off of that, I can add it in this formula and I can get the value. Okay, same goes for a square cylinder or a cube if you want to solve for that. So same, my cube is in this way, and this part is hollow. This is hollow, so it's a square cylinder. So in that case, I will have to know the height of my, or in this case, breadth of my cylinder, and the depth, the height in this case, okay, in the Z direction. So this face, that is directly in contact with the flow. So I'll have to add the area of this face. So if it were a rectangle, I would have to know those values. If it is a square, then it's the same for length and breadth. So it's either way the same. Okay, so in that way you can add, yeah, this is for calculation. So coming back to this. So in this case, since we have a circular cylinder, you can calculate this reference area based off of that formula, 2 pi RH. So in that 2 pi, you get the calculation for that. R, that is the radius, in this case is half of this, so 0.5. And the height or the depth of the cylinder, how will you know that now? Okay, so if you already know that, you can plug it in. But in case you don't know what depth you've given, okay, so you can either check it in your block mesh. So over here, my point is starting from 0 and it is ending at 0.1. So I know that my depth is 0.1 meter because I haven't added any scaling factor. This is one way to find out. The second way to find out is to run block mesh. So the very first thing you can do is do block mesh. You can do block mesh. Once you've done block mesh, you can open it in ParaView. Yeah. Okay, so in case you don't know the depth of your geometry or your domain, you can check it under the information tab. So usually when we click apply, it is in the properties tab. There's a small tab besides it, information. That will give you all the information under bounds. Okay. Yeah, so under bounds, you will get all of the information. So the starting point is at -10 in the X direction, whereas the ending point is at 30 in the X direction. Same goes for Y, -10, +10. And the Z direction, it starts at 0 and ends at 0.1. So my total distance is around 0.1 meter. So I can add that to this equation or the formula that we had. So 2 pi r h. So r was 0.5, h is 0.1. Based off of that, you get this particular value. Okay. So once you have plugged in your reference area, reference length, magnitude of velocity, all of these things, and also the patch, because the patch is the most important part. If you don't add the patch at which you're computing, your simulation will run, but it won't compute it on that patch. So always make sure that the patch name is correct. Now in this case, you saw that it was cylinder 1. So it wouldn't have computed anything for forces. It would directly compute everything for force coefficients. So always make sure you double check these particular things in when running these simulations. Okay. And coming to the block mesh, now the mesh itself, I have it loaded over here. So this is your mesh. Now this is it's a typical case when you're running a cylindrical case. What you will do is you will always set your walls, your inlet, outlet, and the top and bottom at least 25 times that of the cylinder. So that is ideally the safest way to avoid any fluctuations. There's also a paper on that, whether on how much distance is required for a case like this. So it was a simple flow over a cylinder only, I think they had done it for. So in that they varied the distance. So they tried it all the way from I think 5 to 30 or 40, and they saw whether it affects the results. So they found out in that paper that around 25 times the cylinder or your object diameter or the object size is ideal. So 25 times in all of the like the top, bottom, and inlet, whereas downstream it was more. So that was the thing. If you require that, I can share that in the documentation tab in the drive, so you can have a look at that. So this is the typical domain that you would have for a simple flow over a cylinder. And if you switch to the mesh, you can see that there is a nice O grid around the cylinder. So this is a good enough mesh, and it's not too fine, not too coarse. So for our particular case, it's fine because we just want to run it quickly and see how to post process of it. So when you're doing something like this, it obviously takes a lot of time because in block mesh, you don't know what you're doing. You have to visualize everything on a pen and paper. So that is one downside of it, but you can get pretty good meshes when you're working with block mesh and you know what you're doing. Okay. So again, over here, the grading and all is perfectly fine. And you can see that downstreams and even on the top areas, we don't really require that fine mesh because this part we are just not interested in. We are more interested in what's happening closer to the cylinder. So that's why we have a finer mesh closer to that, and we have accordingly added grading to that. Okay, so this is the mesh that you have. Yeah, and now you can go ahead with running the simulation. So for everyone who's doing it on OpenFOAM 2412 or even on OpenFOAM 9, first you create the mesh, you type in block mesh. So I will do that once more, clear. So the very first thing you have to do is type block mesh. Okay. So you can see there's around 74,000 cells. You have all of your general you have all of your information, general information of your mesh or your domain. So you have inlet, outlet, top, bottom, cylinder, and default faces. So default faces are the front and back. And those are the faces that even if you don't define anything. So if I show you the block mesh, yeah, so these are the amount of blocks that I have used. So in total, we have used around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, around 12 blocks to create this domain, okay, with an O grid. So again, you have to, once you start using block mesh, it won't look this daunting. In the beginning, it looks scary, like what exactly is happening here. There are so many numbers and all. And how do I give grading? So again, this is the tab where you add your block. This is the tab where you add the number of cells. This is the type of grading you want to add, simple grading, multi-grading. And this is the place where you add your grading, okay? And if you want to do something like a circular cylinder, you will also have to specify an edge. So over here, the edge, under edge tab, you can use a different type. So in this case, we are using an arc. So an arc in simple terms is you specify the starting point and ending points. So you would define these in the vertices. So this is my vertex number 13 and 12. Between that, I want to add this point at a distance of -5 in the y direction. So that is what I'm doing. So I'll add this particular point in the y direction between 13 and 12, and then block mesh will create a nice arc for me. So the similar way we've done that for the z direction in the z depth. Same goes for all the other parts. So we'll have in total 1, 2, 3, 4, 1, 2, 3, 4. So total 8. 8 and 8 in the front, 8 in the back, because we have a circle and then we have an O grid around the circle. So that is for edges. And then we have the boundary. So over here, you see that I have defined the inlet face or the inlet boundary. So all the faces or all the blocks that consist of that face for outlet, for top and bottom, and for cylinder. For cylinder, I've put as wall. For top and bottom, I've added the type symmetry, not a patch. Okay, so over here again, as I said, that patch is when you can apply boundary conditions to it. So if you want to add a custom boundary condition, or you want to add coded fixed boundary conditions, or even a normal boundary condition for inlet and outlet, that can be done in patch, type patch. Whereas specific boundary conditions like symmetry, symmetric plane, wedge, then you also have wall. So now a wall boundary condition is the very commonly used one. So the wall one, you can add wall functions to it. So if you're working with turbulence, then you can add specific wall functions to that. Whereas for symmetry boundary conditions, if you want to replicate something, so if I want to only create half of my domain, so if I have a symmetric domain, for example, a flow over a cylinder, but this time it's compressible flow, so there'll be a shock wave. So the shock wave will be symmetric in both the upper half and the lower half of my domain. So I need not mesh my entire cylinder. I can only mesh half of it and then replicate it or project it in the negative direction. Okay, so that can also be done. So that is where you use symmetric boundary conditions. Now in this case, I've used symmetric boundary conditions just to explain what I just did just now. There's also symmetry plane. For some versions, you might find that over there. So instead of symmetry, there is symmetry plane. There is also a wedge. So a wedge will allow you to create, say, a section or a section of a pipe or of a 3D pipe. So say you have a 3D pipe, but you don't want to simulate the entire 3D pipe. So you can take one section or a wedge out of that pipe and you can simulate that as well. So for those conditions, you have a specific type named wedge. WEDGE. So this is the type. There is a spoken tutorial on this, so you can check that on how to implement the wedge boundary conditions. It's for a CLCD nozzle. It's for a CD nozzle, sorry, a convergent divergent nozzle. So you can check the tutorial for that as well. Okay, so you see that we have inlet, outlet, top, bottom, and cylinder, and we haven't added anything for default faces. Okay, so, and we haven't added anything for front back also. So in OpenFOAM or in block mesh, if you don't specify a face, by default, block mesh will assign it a default face tab. Okay, so you will have a section named as the default faces, and under the default faces, it will add it as an empty type. So you can see default faces. This is the face that is created by block mesh, and the type it assigns it is empty. Now you can also change this. So there are ways in block mesh in which you can change this. So instead of assigning it a type empty, you can make block mesh say or assign it a type wall or a type patch as well. Okay, so I think in Paris's case, he had one of the cases in which you can open the block mesh and you can check in one of those cases. There is there is a section for adding a custom type also for the default faces. So you can do that as well. Okay. So this was about the default faces part in block mesh. So you have inlet, outlet, top, bottom, cylinder, default faces. Okay. Okay. What denotes the number in bracket in arc? Okay. So for arc, yeah, this one. So for arc over here, so this part, so I'll tell you the syntax for this. Okay. So this is going to be arc, that is the type you're going to be using. Then you type in the starting point or point number 1, point number 2. So this is vertex number 1, vertex number 2. That will be point number 1, point number 2. And between these vertices, this will be your XYZ coordinate of the third point. So the point at which the arc is going to happen. So like it's going to start from 13, end at 12, at a distance of what that is defined by this particular value, XYZ coordinate system. Okay. So I hope that answers your question, Mr. Vednath. Okay. So going back to the terminal. So I hope everyone has done block mesh so far. So if you've done it, yeah, just give a thumbs up or raise your hand, or you can speak also. Yeah. Okay, fine. So now once you are done with block mesh, you can again run this as simple form. Again, this is a pretty simple case, so you can run it as it is. Now, if you see when it is running, you can just use simple form. It will start logging things. So usually it will just say time. It will give me some data on the solver. So it has your initial residuals and all of those things. And then it will go ahead to the next one. But in this case, since we have switched on the logging of these force and force coefficients in, okay, this one. Yeah. So force coefficients in the terminal. So it will start showing all of these values as well. So you can check the values over here as well. So the sum of forces. So you have total pressure, viscous force. So all of these values in the XYZ coordinate system is given. Okay. Yeah. Same goes for the force coefficients. Force coefficients also, it will give me pressure, viscous, internal. Then it will give me CD, CDF, right? Then it also has CL, and it has then coefficient of this coefficient of moment coefficient, and then for that, for pitch, roll, yaw, and all of these things. So all these values are logged over here. Additionally, now this is already run. Okay. So if you remember, when we were running the ART foam case, you saw that it ran the case. But if I don't know if you noticed that over there, we also had this folder named as post processing. So when you add these functions in the control dict, so now in this case forces and force coefficients, when you run your simulation, it will create an additional folder named as post processing. Okay, so if you open this post processing, so all what you saw in the terminal here, all these files, all these text that is logged over here, it is saved under these files. Okay, so you have folder of force coefficients and forces as well. So I can open force coefficient under 0, and then you have this coefficient.dat. Okay, so let's open this. So you see over here, I'll just change the text. Yeah. So over here in the beginning, it will give you some of the data that you've already set in your control dict. So drag direction, it will give you then side, lift, roll, pitch, yaw. Then it will also give you the velocity that you set, magnitude of velocity, reference length, and the area reference that you have set in your control dict. After that, it will start logging your file. Okay, so it will start with time. So at every time step, it will, now in this case, it is set to our delta t. So if our delta t was 0.1, it would start logging from 0.1, 0.2, 0.3. But in this case, it's 1, 2, 3. So it's logging based on that. Then it will log your CD value. So this is all the CD value that you've got. This is CDF, CDR, and then you have CL. So in this case, we're only interested in this particular CD, this particular columns, coefficient of drag, this one, coefficient of lift. The F and R can be ignored. And if you're interested in moment coefficient of pitch, roll, yaw, you can also check those. Okay, but ideally, general public are always interested in just coefficient of lift and drag. So these two are the values that you have to keep in mind. Okay, so I'll show you the significance of this file, of generating this file. Okay, so this is the file that you will get once you run your simulation. Okay, so has everyone ran the simulation and have reached to up to this point? Yeah. Yes, Jitendra. Okay, you've raised your hand to tell that you're done. Okay, 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 fine. Yeah. So now, once you've run the simulation, okay. Now I said that you can do the simulation one way, and then you can post process it in 3 different ways. Okay. So now I'll talk about one of the ways. The first way is the simplest one. You can open ParaView because you have that app, and you can start post processing on that. So let's see how to do that first. So first, just type parafoam. Yeah. So once it's loaded, click on apply on the left hand side. Okay. And once you click on apply, you can change from pressure to velocity. So on the top corner over here, you have pressure is set to P, change it to U. Okay. Once you set it to U, on the top, you have this play button over here. So you can click on play. Okay. So now you can see, I'll zoom in. You have a nice flow over a cylinder and you have some vortex shading behind it. Okay. So is everyone able to do up to here? Load the file, .foam file, and see U and P. Okay. In case you cannot see U or P, just scroll down. Now it depends on OpenFOAM 9 or on OpenFOAM 2412. There will always be this cell arrays. So in case these are not ticked for U and P, make sure it is clicked and then you can hit on apply and then again load. Then it should show up over here. Okay. So this is for people who are facing problems in loading the file. Okay. Yeah. And in case for people who have again problems in loading the file, so say you're not able to load the file, like how I was like the problem that was happening to me just day before yesterday. So you can do touch and then you can name it whatever you want, fdp26 dot foam. Okay, so you can type this command touch whatever name you want to set dot foam. You can also type touch foam dot foam, and once you do this, it should create a file named dot foam in your folder. So you see fdp26. Yeah. So Kalyan, if parafoam isn't working, you can manually open parafoam. So that's why I said for people who are facing problems loading paraview, you can type this command touch, and if you want, you can add your own name .foam file. And once you've done that, it will load this particular file in your case directory. Okay. Now once you've done that, you can go to your Windows search, and over here you can search for the version that you have separately downloaded. Okay, so in my case it's paraview 5.12. So once you do that, it will prompt you to open the paraview. So in my case I'll have to wait for some time. Yeah, so I'll just change the scaling. Yeah, so once you've opened paraview in this case, you can then right click and open. So once you right click and open, what you can do is you can go to your file. So this is your file structure, and the path at which you are, just right click it and copy address. Okay, so Mr. Ganesh, you will have to extract your file and then copy it into your run directory. Just extract it as you would always do for a normal file, zip file. Okay, yeah. So moving on. So once you have copied this particular path, so you can just right click this top path. If you're on Windows, you can right click it, copy path or copy address, and go back to parafoam. Once you've clicked on open, you can just paste the path over here. Look in, it will show over here. Look in and paste it over here. Hit enter. Yeah, in my case, it isn't giving that. Fine, we'll go one directory on top. Okay, now you can manually, in case you don't have recent, ideally it should open over here, but in case you have problems, you can manually open it from here in the file structure. Okay. So in my case, it is under tutorials OpenFOAM 2412. So I'll go to 2412, run post processing and scroll down and then open this .foam file. Okay. Santosh, which files do you delete? And click on apply. So if you have any old files that are already there with the same name, you can delete it, or you can just add them into a separate folder. Like usually what I do is, if I have multiple files that have the same name in my run directory, I copy it into a dedicated folder like this, and I just dump everything inside that. So that way it does not interfere with any of the tutorials. So I have a new tutorial within this. So that way it does not interfere. Okay. So you can also do that. If it's a simple tutorial file, then you can always delete that. If it's something important, then it's better to put it into a separate file as well. Yeah. Okay. So once you've loaded this in in ParaView, then again you can click on apply, and on the left hand side make sure that your U and P are clicked, and then go to velocity, and then you can, once you hit on velocity on the top under U. So again, there's a difference between the U with a dot and the U with a square. So if you click on U with a square, it will give you the cell data. So if I zoom in now, since I have a very fine mesh closest to the cylinder, it will play it. Okay, so the U with a cube is your cell data, whereas the U with a point is your point data. So you can see that over here, the resolution is not really nice, because it's if you see the mesh view, it will show you each of the value in these cells. So what is the cell value at that given time? It will show you that if you click the box one, whereas if you click the point one, it will give you a smooth one. Okay. So this is your flow over a cylinder. Now let's see how to post process off of this. Okay.
Ivan sir, sorry to disturb, but can you
Yeah.
show it again
Yeah,
how
yeah.
to click on the
Yeah.
cell arrays?
Sure. Yeah. So again, I will show you again from the beginning of how to open this .foam file. So for people who have problem opening the dot or opening ParaView, you can physically search for in your Windows search for ParaView, the version that you have downloaded, and then you can right click and open. Once you have right clicked and open, you can check under recent, or you can manually search it in this locations, and you can scroll down and then click the .foam file. Click on OK, and the green button on the left hand side will show. Click on that, apply. Okay, now once you've applied it, so on the top you will be able to see P, change that to U. Okay, now again over here in this tab only, when you click on U, there are different options. So you have P with a cube, you have U with a cube, and then you have P with a dot and U with a dot. So the dot ones are point data, whereas the U one are cell data. Okay, so you'll see why we use point data and cell data and what is the significance of it when we're post processing. That makes more sense. But for now, if you want to just see the cell data and you want to see the simulation for cell data, you can click on U with a cube and then hit the play button on top. Okay. So once you hit the play button, it will give you all the values or the data for each cell in this. So it will show you the cell data that is being displayed. And if you want to change it to the point data, then you can change it to point data. Okay. Yeah. So now since this has run for around 50, it has for around 500, so that they're logging it at around 10 seconds. So that's why you only have 50. If you want more files, then you can obviously reduce the write time to say 1 or 2, and then you can save all of those files. But just keep in mind that more amount of files takes more amount of space. So just keep that in mind. Okay. Now you have, so far everyone has done, right? You've loaded the file, opened up U, and kept it at this, correct? Yes. Okay. Now we'll start with post processing for coefficient of lift. Okay. Before going to the actual coefficient of lift and all, I'll show you some basic post processing tools that are present. Okay. So the tab under which you click this U, okay, just below that there is this nice ribbon, a long ribbon. Can everyone see that? This one, you can see where my mouse is. Yes. So under that ribbon, you have many functionalities. If you cannot see the ribbon, you can always search all of that. Okay. So the very first thing is a calculator. The second one is contour. The third one is a clip. The fourth one is slice. The fifth one is threshold. Now threshold, we don't really use it. It's only for very specific cases. then you also have other options that are not uh, available. That is because you require or you need to set some filters, only then they get available. Okay. And then you have glyph and streamlines. So by far the most common ones are slice. If you're running a 3D simulation like you saw in the morning when we ran the 3D room simulation, so in that you saw me taking a slice. So that is how you can do, you can take a slice. But in this case we have just a simple 2D geometry, close to 2D geometry, so we don't really need to take a slice. So we'll see these two options just below you, streamlines and glyph. Okay, so if you click on streamline, so there are two ways to search this as well. Okay, so streamline, you can either click the option that is already present over here, or on the top where you have file, edit, view, sources, all of those things on top. Okay, over here you can click on filters and you can click on search, the very first option, filters, search. Okay, when you click on search, it will give you this box and you can directly start typing. So in this box, if you cannot find any filter or you wish to find something new, you can type in over here. Now in this case, I want to search for streamline, so I'll just type STR. Okay, so now you see I have so many options. I have streak lines, I have streamlines, I have stream tracer with custom source distribution. So all of these options are there just by typing STR. So over here, you can then click on stream tracer. Okay, once you click it, you can hit enter and then it should give you stream tracer. Okay, is everyone able to at least find or click stream tracer for now, or streamlines? Okay, okay, good. Now don't hit apply yet because we have to make some changes. Okay, now in streamlines you can change between point data or cell data. Again, this is your choice. If you want, you can use cell data, you can use point data. For now, I'll keep it at default. It's set to point data. Integration, direction, both you can keep it as it is. You don't touch the first few tabs. So integration, integration type, integrator type, those just leave it as it is. Okay, now maximum stream line length, that you can change it. Like if you have a very long geometry, you can change that, or you can that is for if you're using this line. You can see the small point over there's actually a line running through the entire domain. Yeah, so you can see this line. Now that is because we are going to be plotting or removing the streamlines over this line. Okay, so I'll show you the difference between using the line option and using a sphere option. Okay, so this line option that is there by default, what it selects over here under seed type, you have this seed type. Can you see this? Under seed type, you have this small drop down menu. You can change between point, cloud, or line. Okay, so by default it is set to line. If you click on line, it will ask you to set the limits of your line. So in this case, my point 1, that is this one. So you'll have to give the coordinates of this lower point, and then you will have to give point 2, that is coordinates of your higher point. Okay, you can also set it manually, like if you want to just set it along the X direction. Below that you have these options of X, Y, Z. So now you can see that my line has been oriented in the X direction, whereas over here it is oriented in the Y direction. You can also do it in the Z direction. It's in this way. Now Z direction is very small, that's why you cannot see. Okay, so if you want, you can do it along X, Y, Z, and then you can click on apply. Okay, so now you see that you have this streamlines. But now if you have a 3D geometry, now this is a 2D geometry, so it makes sense. Okay, and just below this line, there's also a resolution option where you clicked on length. Okay, so below that it will be set to 1000. I can change it to 100. You can set it to 10,000, 10,000, 100,000, anything you want. But just keep in mind your system should be able to handle that. Okay, yeah. So I'll repeat that again, Harinder. So once you've loaded your stream tracer, the very first thing you do is you scroll down. You'll have this option of seeds. Okay, so the seeds, you can click on the line option, seed type, line, click on line, and then you can, if you want, you can change the points. So you can manually drag these points as well. So if I want to change it, say like this over here at this point, if I want to add this and this point, you can see you can drag it as well. But if you want to specifically add a point in a particular okay, I hanged with resolution. So yeah, just give me a second. Okay, so you can add these points anywhere you want. Like you can drag them and add them anywhere in space, and you can then plot over it. But if you have a geometry and you want to specifically find something, you can always use the X, Y, Z. So it will orient it based on that axis. So in this way, I can change it based on the X, Y, Z. And you can also mention the lower end, the lower part of the point, and the higher up, like the second point, the lower limit, upper limit. So X, Y, Z coordinates of these. Now, for people who are having problem with the paraview hanging or something like that, change the resolution from around 1000 to 100. So that way it should help you with the hanging thing. Because if even I type it, I type like resolution around, how much is this now? Units, tens, hundreds, thousand, 10,000, lakh, 10 lakh, crore. So this is around 1 crore. Okay, so it becomes really difficult. So even my system will start to hang on this. Okay, so make sure that the number is reasonable based on your computer specs. So the resolution in this case, I've kept it to 100, and then I can hit enter and click on apply. Okay, so once you click on apply, you will be able to see these streamlines. If you want, you can also switch off the line. So on top, where you were clicking the coordinates for point 1, point 2, there's a small tick mark or tick bar that allows you to show line or not to show line. So you can switch that off. Okay, so in this case, I'll just switch that off. And now I cannot see my object. So if I want to add this to, say, if I'm doing some research and I want to add that in my research paper or something like that, I need the geometry itself. So you can do one more thing, is the .foam file. By default, it will switch off, like it just gets hidden. So you can switch that on. There's a small eye icon beside it. You can switch it on and off. So you can switch that on, and under the surface, where you click on surface with edges and all that, you can go on top and click on feature edges. Okay, so feature edges, that will show only all the edges that have a feature. So in this case, edge, and we can click to solid color. So you can see it in white. And the streamlines that you have, now the streamlines, you can see that over here under the drop down, it has been colored according to the pressure value. So you can change that to velocity. Okay. So now I have my streamlines around my cylinder. So you can see these are the streamlines. So this is one way you can do. The second option that is there. So again, I'll show this line. Instead of, now if you have a 3D geometry, you cannot use a line always, because the line will try to plot everything closest to that. Okay, so in a 3D geometry, you have something known as a point cloud. So if you click on a point cloud, it will generate this cube, this sphere around your geometry. Okay, so you can see the sphere, big one. So now, once you have this sphere, again, you can change the orientation of the point. So you can move the sphere, you can drag it and move it if you want. Now in this case, I will just set it to 0, 0, 0. Okay, so I've set it around my cylinder. And you can also change the radius of the cylinder. I'll just increase this thing. Yeah, so you can change the radius. Under radius, you can change it to say 5 to 10, maybe 50. Yeah, 50 becomes too big. 20. Yeah. So the main idea of this sphere is that if you have a 3D geometry, and if you want to compute or calculate or find the streamlines around within that entire geometry or around that geometry, it is always better that this sphere engulfs your entire geometry or your entire domain if you want to find the streamlines in that particular case, in a 3D case. So in this case, the sphere, I will make sure that it is almost covering the area of interest for me. And then I can again change the number of points. Now in this case, points is 100, and I click on apply. Now when you're using a sphere, what happens is that since you're computing it in 3D space, the number of points need to be changed a little bit more. So now in this case, 100 won't do. Let's try 1000. 1000 also is only showing a few streamlines. Let's try 100,000. Apply. Yeah, you can again switch on and off this sphere. So in this case, you can switch it on and off, and then you have your entire domain. So the reason for using a sphere is you get a little bit more cleaner streamline. So in this case, you can see that in the previous option, if you were using the line, the streamlines tend to move out of your domain and they try to plot, because you have to specify something like the length of the line itself. So that is also there. So it tries to take more of what you're actually giving. So that way the line takes some more resources as well. The sphere itself, you can tweak that, and you can also use it for 3D. Yes. Yeah. So for 3D, I'll show you one particular file. So I'll switch these two off. Yeah, for 3D. Yes, Satyam.
Hello. Yeah,
Yes.
so what you're saying is that imagine if I have a room and I want to see the flow around with the streamline, so I can simply put that sphere inside the room and then I can see the flow. But can I do the same with like cutting the plane and then making a line also?
Yes, you can do that as well. So that I'll demonstrate that over here. Okay. So now this is
Okay.
the morning case that we had, the room ART form 1. So in this, I will now do streamlines. Okay. So now if you see, by default, it will take this starting point and this is the ending point. So I'll just lower the opacity. You'll be able to see that. Yeah. Yeah. So you see, it's taking this way. Now, if I were to just hit apply, yeah. So you see, it is trying to take all the streamlines in within just that line. Okay. So if I want to find out what is happening in this corner, I'm not able to see that. So that is where the sphere comes in. Okay. So you have this point cloud. Now I will change this point cloud to say 5. So it's engulfing my entire domain. You can see. And now I hit apply and I'll increase the number of points. So say around 1000 or something. Okay. And I'll switch on the sphere. So in this way, you can see that there is this. If you want, you can also change the color. So in this case, I want to change it for velocity. I'll change 1 minute. I'll change the velocity color a little bit different. Rainbow. Apply. Yeah. So you see in this one, now you can see the flow. It is entering this, like this is the area where the door is over here. Over here. This is the door. Whereas this was the AC. So if you see, I'll increase the number of points as well. You'll be able to see it much better then. Yeah, okay. Okay. Yeah. So if you're able to see over here, I'm not sure if you'll be able to see it clearly. Yeah. Over here where the AC is, you can see that there's the flow that is happening in a slant direction towards the downward direction, right? You can reduce the upper limit. Yeah. Yeah. So you get the idea, right? So if you want to simulate something or you want to capture something within your entire 3D geometry, you can use the point cloud. So again, for these kind of cases, having the point cloud makes more sense, because you saw that in the line, it was just trying to fit everything closest to the line. Okay. So I'll keep this also open only in case, yeah, if you want, you can switch that off. So this is just for the domain. This is inside. Yeah. So over here, you can see it in depth. Yeah. You can see that the flow is happening this way. It hits it, then it circulates around. Yeah, it circulates around and then it goes, everything is going out the outlet. Yeah. So you can see this on your own system also. If you've ran it, you can obviously check this out. That's why we shared all the files. So you can obviously take all of these files, run it and explore it yourselves. So this is for the 3D case. Okay. So coming back to the, yeah. 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 And on top over here, you have just to change the orientation. So if you want to change the orientation in the positive Z or negative Z, positive Y or negative Y, so you can change these orientations based on that. Yeah. Okay. Now, this is about streamlines. Then you can also see glyph. So just beside streamline, there is something known as glyph. It's like a spear. So you can click that. Okay. Yeah. So when you click on glyph, again over here, it will give you some options. So the glyph, you can change it to arrow. You can change it to cone, box. For now, I'll show you for arrow what happens. So when you click on arrow, you will have down option for orientation and option for scaling. Okay. So now, if I'll close the streamline. Okay, for now I'll just show you glyph. So if you click on velocity, so the orientation will be based on how your flow is happening. So in this case, the flow of velocity. So if my flow around the cylinder is going upward over here, closest to the wall, it will orient the arrows in such a way that it is moving that way. And scaling will scale it based on the intensity of the flow. So if I were to say that over here, or closest to this boundary of mine, the top boundary condition, closest to that, the flow will be uniform. So it might happen that the flow is around 1 meter per second over here, whereas behind the cylinder, it is just 0.1 meter per second because of the recirculation zone. So in that case, over here, the arrows will become a little bit more smaller. So I'll show you. Let's open it. Yeah. And scale factor over here, you can change the size. Scale by magnitude. Yeah. So you see over here, the arrows are a little bit smaller. Yeah. Under the glyph. So these arrows are small because the flow over here has the least amount of velocity because we've scaled it based on velocity. If you click on new scale array, then it will just orient everything based on velocity. So the direction of velocity. So you can always scale it down, scale factor, so that way the arrows are smaller. Okay. So you can see over here, there's some circulation. So the flow is happening this way, but over here, there's something turning back again. You can scale it down even further. Can apply. Yeah. And then you can click on scaling array. Yeah. So in this way, you can see that here the flow is really slow. So if you're running a 2D channel or you want to find out boundary layer formation, it can be any, it can be flow boundary layer formation or even thermal boundary layer formation. If you want to find out the intensity, the direction of of how it is happening, you can always use this glyph option. And in the morning, I'd also use this glyph option to show you for the 3D case. So in this case, the room case that was there, I'd shown you how to check for glyph as well. So click on glyph, no scaling array. Yeah, so this is the flow that is happening within your domain. So you can see it's like all over the place inside. So this way you can check glyph. You can also do this on a slice, like you saw in the morning. I'd taken a slice and then I'd applied the glyph on the slice. So that is one way you can do. Now, if you see this, the flow chart over here that is there, you'll see that all of this is applied. So I'm applying stream tracer over .foam file, glyph also over .foam file. If you want, you can also change this. Okay. Yeah, you can also change this. So change input. So over here, say if I want to change this glyph, I want to add it for the streamline. So I can click on streamline, click on OK. So now my glyph is applied to streamline and streamline is taken from .foam file. Okay, so it will start applying all of the parameters that I set under glyph for streamline. So this way you can change the input parameters. Okay, so we are done with streamlines. I showed you how to do glyphs. So again, I'll just repeat once again. Glyph, you can just click. Make sure you're on the .foam file. Once you hit on glyph, you can check arrows. You can change it to cones also. So now in this case, you saw that there were arrows. You can change it to cones, boxes, cylinders, lines, spear, 2D glyphs. So all of those are possible. Orientation for velocity. For scaling, you can either click on no scaling array or you can click on the scaling array for velocity. And you can then use the scale factor to change the size of the arrows. So that is your scaling factor. And also you can change the maximum number of sample points. You can change that. And you can also change seed value. So again, this will just change how many arrows are there or how less arrows are there. So it's just that value. Okay. So in this case, it's all on the streamline. Okay. Yeah. So I'll just have water. Excuse me for a minute. Yeah. So this was about stream tracer and glyph. Now let's see the slice option. Okay. So for this, I will switch to the 3D case that we have. So this is a 3D case. Now say I want to take a slice within this domain. So on the left hand side, you can see that there's a slice option over here. So there are two, one is clip, other one is slice. So slice will just take a simple slice in your entire domain. It will just take a piece or a plane out of that 3D domain. Whereas a clip, it will cut your domain into half. Okay, so I'll show you clip. So say I want to clip only half of this. So I'll orient it along the Y and I'll change this position just to show you. And now if I hit on apply, so you see it has clipped the top half. So the top half has become transparent. So I can see any flow or anything if I want to see. So in this case, we'll see velocity. So it will apply the value, whatever I choose, the coloring only to the bottom half. And the top half will just remain transparent. So in this way, you can see your entire domain and you can also see the clipped part. Okay, so this is for clipping. You can again change the orientation. If you want, you can invert it. So instead of showing just the bottom half, you can click the top half. So again, if I click on invert, on apply, it will show this. Okay, so this can be done. So this is for clip. I'll just delete this and we'll see slice. Okay, so now slice, it's just the option beside it. So click on slice. Again, just scroll on top if you will. Again, over here, you can click on box. You can click on cylinder. You can also click on plane. You can also click on sphere. So depending on how you want to clip it or how you want to slice it, you can check. The most simplest form is the plane one because usually you want to check a particular plane in your 3D geometry. So in the plane, again, similar to the line one, stream tracer, you have these options of show plane. So if you want to see the plane, you can see that. Then show outline. So again, if you want to see the outline, you can switch that on and off. Then the origin. So again, lower limit, the origin of this. So this is going to be the center point over here, this point. The normal. So now this normal will show in the X direction. Now it is 1. So if I were to change it at 1.3, let's say 2. Yeah. So again, over here, this will see your XYZ coordinate. If you want to just use one of the pre-existing axis that is there, so you can click on this X, Y, Z. So it will orient it based on that. Okay. In this case, I will click on Y. You can physically pick or you can physically move this up and down like this. Or you can also just hold the arrow. So don't hold the point and move it. Okay, then it will start moving the point. This is your center point of rotation. So if I were to move this over here, and now if I were to take the arrow and yeah, so you see that is the point of rotation now. So don't move this arrow if you don't want to move it. Just touch the plane. So if you just want to move it up and down in that particular axis, just hold the plane and move it up and down. If you want to just change the orientation along the rotation of along the axis of rotation, you can move that as well. And if you want to just change the point of rotation, then you can do that. You can hold the point and then move it. Okay. So once you have taken the plane, so in this case, we'll take the plane something like this. Then you click on apply. Okay. Now you have this plane. If you don't want to see this plane, you can just switch it off. And now you can apply the coloring that you want. So in case you want to see the scalar field in this case, you can see that. If you want to see the velocity field, you can see that. If you want, you can also apply stream tracers or glyphs on this plane. So just make sure that you are clicking the slice. So you can apply the filter on any of the other filters that you create. Okay, so in case I have created stream tracer, glyph, and then I've created a slice, I can add stream tracers on the slice as well. It's not restricted to only .foam files. There are certain this there are certain filters that require you to only apply it on particular. If I remember correctly, this is screenshots. Let's see under filter and search. Let's search for animation. Yeah, animate mode. Enter. Velocity U. Can apply. Yeah, okay. But I'll have to check. I used to use animation, but I've forgotten. Yeah. Okay, I'll check about the animation part. And if we cannot find it during the session, we'll email you that. So it's not a problem. Yeah. Okay. Can we define n number of data points at once and visualize data of all the things? Yes, you can define n number of data points. You can open files and you can apply filters to it, and then you can also view each of those filters results in the spreadsheet view, and you can download that as a CSV. You can do that, but I don't get your question completely. What do you mean by n number of data points? For CL and CD, you'll see how we save the file and all. So that I will show you. That's not a problem. Yeah. Okay. Yeah. So if you want to extract that data over a line, I'll show you that as well. Okay. So we have for that plot over line. So for now, I hope you've understood stream tracer, glyph, and slice. Okay. So these are all for visualization purposes. They are not specifically for extracting data out. Okay. Now coming to, okay, I'll delete all of these since we don't need that. Delete, delete. Yeah. Yeah. Okay. So now, say we want to do, okay, let's do it for this one. So 2D case, it's okay. So velocity. Okay. Now there is something known as plot over line. If you want to extract data, so that can be found on the top ribbon again, where we were clicking for glyph, slice, all of those things. Just on the right hand side, there is this box with a line on it. You can see it over here. It will, if you hover over it, it will just show you plot over line. If you cannot find this over here, again, you can go to filters and you can search. So over here again, search plot over line. So you have multiple options. You have plot data, you have plot data over time, you have plot global variables over time. Again, intersection curves, plot over line is there. So we can just click on plot over line. So there are many options when you're extracting data. Okay. So we click on plot over line. Okay. Now again, you can see that it has generated this line on top. Okay. So this line again, you can drag it anywhere you want in your entire domain. If you don't want to do that, you can physically just apply it on the X or Y axis. So I will specify the starting point. So I know that my domain starts from -10 in the X direction. So I will specify -10. And I know that in the Y direction, it is around 10 in the top and 10 in the bottom. So I'll just set it to 0 because I want it to be at cutting through the center of my entire domain. Okay. So when you do plot over line, so you can click on plot over line and you can follow along with this. So you can change the first point to -10, the value for Y to 0, and Z keep it as 0.05. So that is like almost within your domain. Okay. So this is for point 1. For point 2, the X point set it to 30 and for Y set it to 0. Okay. So now it is running through the center of my domain along the X axis. Okay. Is everyone able to do this so far? Just make the line and give the data for it, the point data. Yeah. Now, once you've done this, you can do apply. And when you hit apply, it will generate this graph. Okay. Now, you can click this graph, just click it. And on the left hand side, you can scroll down. It will give you some more options. So over here, you can switch on and off any parameter that you want. So currently we are viewing pressure and we are seeing magnitude, velocity magnitude. Okay. So you can switch it on and off. And if I only want to see velocity magnitude, I can see this. Okay. So now you see this cut that is there. This x-axis will directly correspond to your direction, your domain size. So this is at 0, then 5, 10, 15, 20. So again, this point is around 10. Okay. So this is your, if you want, you can also manually change this. You can change the axis to custom axis as well. Okay, so that can be done. So in this case, wherever the cylinder is there, there's a gap over there. That's why you have this break in the graph. If I were to move this slightly on top, so at around 10 by 10, not 10, let's take it at 5. Apply. Yeah, so you see now this is at around 5 plus 5. So over here somewhere the line will be there. Yeah, so you see here it is the starting point, this is the ending point. So if I click on this, you will be able to get the graphs over here. So this is for plot over line. How to bring the line to front, it appears behind figure. It's not behind the figure, it's in simple terms within the figure. Okay. So if you want to bring it front or back, that is along your Z direction. So you can change the values for Z. Okay, Abhinav. So if you want to bring it in the front, you can change it in the Z and then it will move ahead accordingly. Okay. For now, it's within your this 2D domain. Okay. Yeah. So this is to plot. Now in case, now you can view this as a graph as well. So this is your graph data. If you want to export this value out, you can click on the top of the graph. So over here, when you have this graph selected, you can just click on top, right click it and convert to. So when you do convert to, you can go down to spreadsheet view, and that same graph that you saw, it is now in a spreadsheet view format. Okay, so you can see all the values are over here. It will also give you your point data, your arc length and all of those things. And then at the end, you can also see U magnitude, velocity, points, and there should be one more, pressure. Yeah. Okay, and say you want to export this, you can click on the top just below this thing that is written spreadsheet view 1. Just below it, there is this small tab named as export spreadsheet, this small icon, just click that. Okay, now this small tab will save it as a .csv file. So again, over here you can type, say, result.csv and you can save it. Okay, number of precision up to 6 points it will save. Then you click on OK. Now, if I load my file once more and I scroll down, now I'll have this. Okay. Okay, I saved it in the, okay, I saved everything in the wrong location. So we'll do it again. We'll save it. I saved it in the air RT file. So we'll go to post processing. We'll save it in the correct file. Okay. So don't make the same mistake as me. Make sure you're saving it in the proper location. Otherwise you'll be searching for it. So under result.csv. Okay. So you click on enter and then you click OK. So now if I go and I reload my file and I scroll down, it should be over here. Okay. This result.file. Okay, so now you can open that. You can view it in Excel. If you want, you can also do post processing over here. So as I said, you can use 3 ways: ParaView, Excel, Python. So Excel over here, you can just plot. If you want to just plot U versus P or U versus time, you can do that. You can select the velocity tab, you can select the time tab, or you can create a time tab, and you can then make the graphs according to that. Okay. Yeah. Yeah, I will use the calculator tab when we are calculating for this CL and CD. Okay, so this was plot over line. Okay, so now you know how to plot over line, you know how to see the graph, and you can also convert that graph to a spreadsheet view and then extract that data. Okay, so for now I'll just close this, and plot over line, we don't really need it now, so I'll delete that. You can keep it if you want, it's up to you. Now, so we've seen clip, we've seen slice, we've seen glyph, we have seen also stream tracer, and lastly we saw plot over line. Okay, now coming to the actual case. Okay, so we have this flow over a cylinder. We have ran the case, we've got some vortices that are there, and now we want to calculate the coefficient of lift, let's say. Okay, so let's take coefficient of lift for this case. You can do the same for coefficient of drag as well. Now, so first you have to make sure that you're picking the proper file. So in this case, it is this .foam file of mine. Yeah. So Jitendra, I will speak about the custom functions as well. So towards the end, I will talk about that. Okay. Yeah. Yeah, you can, Irshad, you can copy all of this data in TechPlot as well. That works fine. And if you have any data and you want to plot it using Python as well, you can do that as well. So for Python, you have to specify a Python code. So I'll show you how to do that as well. Okay. So coming back to the topic, make sure that you are clicking the proper file. So make sure you have this .foam file that is for your flow over a cylinder. Okay. Now, the very first thing you will do is go to filter on the top and click on the filter tab and click on search. Okay, so everyone do this. Open the search filter, and over here you will type extract block. Okay, so click on extract block. Okay, so once you click on extract block, just scroll on top. Yeah. Okay. Yeah. Okay, it should show some more files. Wait, I'll just reload my file once more. This is the file, right? Parafoam. Yeah. Apply, filter, search, and extract block. Okay, internal mesh, fine. Wait. So we have this cylinder. Yeah. Enter. Yeah. Okay. So when you click on extract block, it should show these options. Okay, so if it is not showing, like in my case when I just loaded it, it was not showing this cylinder. Okay, so cylinder boundary, if it's not showing in your .foam file, make sure that you enable the cylinder patch. Okay, so once you have enabled your cylinder patch in the mesh regions over here, go to filter, under filter go to search, and then search for extract block. Okay, so once you've done extract block, click on this cylinder patch. Okay, cylinder boundary. Okay, is everyone fine till here? Once you've selected the cylinder patch, just click on apply. It will extract this particular block, or in this case patch, your cylinder patch. Okay, so now we're going to do post processing just on this patch or this block. So we've extracted this block out. Now again go to your filters. So there you can either do search filter, or you can go to favorites, or you can go to alphabetical. Under alphabetical, it will show all the filters that are available in ParaView. So these you can search it manually over here, or you can do the actual search. So go to filter, click on search. And now the next thing that you will search for is extract surface. Okay, so let's type extract surface. Let's see. Yeah. So just type extract surface and click on this option. First one, enter. So once you click on extract surface, it will give you, you don't have to click anything, just click on apply. Okay. Now this we are adding this extract surface on the extracted block. Okay, so make sure you're in this thing. You're not clicking your .foam file. So if you're losing track of what I'm doing, just look over here. Okay, so here you have the .foam file first. On the .foam file, we did extract block. In extract block, we clicked on the cylinder patch, and under once you've done that, then we did extract surface. Extract surface was done on extract block. Okay, so is everyone done so far? Yeah. Okay, now once you've done extract surface, keeping the extract surface selected, go again back to filter and go to search. Okay, so once you have gone to filter and search, now you type generate surface normals. Okay, so you'll see why we are doing this, because you have to generate some additional terms for calculating force and then coefficient of lift using those forces. So type generate surface normals and click on this option. Okay, generate surface normals, click on enter. Okay, and over here, once you have generated your surface normals, in this checkbox over here, click on compute cell normals. Okay, this one, so very important. Okay, click on compute cell normals. Once you have selected that option, click on apply. Okay, everyone done so far? Generate surface normals, check mark the compute cell normals. Okay, yes Gino. Okay, okay, fine. Yeah, so once you are done with generate surface normal, then again go back to the filter and go to search. Now this time you will search for cell size. Okay, this one, cell size. Click this and click on enter. And once you have clicked on cell size, you click on apply. Okay, done so far? So you are doing first the .foam file, then you extract the block, then you extract the surface on that block, then you generate the surface normals on this extracted surface, and then you do cell size on this surface normals that you have created. Okay, so far so good. Okay, now the next thing that you will do is, on the left hand side you have this small calculator tab. Okay, now we will calculate the forces that we have on our cylinder. So click on this calculator. Okay, see over here, left hand side, this small icon which looks like a calculator. Click on that, and over here, now attribute type that you have, instead of point data, change it to cell data, because we have extracted the surface normals and then we did cell size. So that cell size is all based on cell data. So we are computing the forces based on the cell data for this cylinder patch. Okay, so first you do is go to calculator, click the calculator tab, then go to attributes type and click on cell data. Once you have clicked cell data, you can change this name over here, result array name. Instead of result, we will change it to lift force. Okay, so I've changed this to lift force, the name. Okay, and now in this we will add the lift force formula. Okay, so lift force is your pressure multiplied by the normals in the y direction and the area, correct? So in this case, if you want to add pressure, you have this scalars option. So a pressure is a scalar, so you will have it under the scalar option. Click on P pressure. Then you can use this multiplication tab. So you can click on multiply, and then you will use the normals again, that is a scalar, because we've generated the surface normals. So click on scalar again and normals in the y direction because you want to take lift, correct? So P multiply by normals in the y direction, normals P, again multiply by the area. So the area is over here. So the area we've extracted it from the surface features, from the extract surface. Okay. So far everyone is done. They've taken the calculator, then they have changed the name to lift force, and then you add the formulas P multiply by normals Y multiply by A, area. Okay. Now once you've done this, you can click on apply. So you can change this calculator name to, okay, P is not showing in the calculator. So make sure first you're in the cell data type, and P will show under scalars, not under vectors. Okay, so make sure that you're under scalars, and it should show because we are calculating pressure from the simulation itself. Yeah. So once you have done this, you can rename this calculator. Just click on the rename of calculator, and you can just click and hold on it, and you can change it to lift force if you want, or you can leave it at calculator as well. Lift force. So I'll just change it to lift force so that I don't get confused. Okay. So now I've just renamed this to lift force. Okay, so far so good. Okay, is there anyone who's facing problems still here in opening the calculator and typing in the formula? Okay. Okay. So Ginu, you're still not able to find the pressure? Point data is showing. In point data, we are not solving for point data, we're solving for cell data. So see, just cross check with the blocks that are over here. You should have .foam file, extract block. Under extract block, make sure you select cylinder. Then under extract surface, make sure you are selecting, you don't have to select anything, but just apply it properly. Then go to generate surface normals. Under surface normals, okay, you're using ParaView 6. For 6, then it may be a little bit different. I'm not sure. Because this one, what I'm showing you, this methodology, it works from 5.6 all the way up to the latest 5 version that was there. For those all I have tested, so it works fine. So you can try reducing the size, the version down. You can come down to 5.1 or something like that. Area is from your generates of, you've extracted your surface, so that will generate your area, and then you have your generate surface normals, that will generate your normals in the y. Okay. Yeah, and if you're not able to see, then again, once you do cell type and all, if you're not able to see area or length or normal x, y or something like that, make sure your attribute type is set to cell data, not to point data. See, if I click on point data, it will not show me anything. See, it will only show me coordinate x, y, z, normals x, y, z, and then p, and then u. It's not showing me length, area, all of those things. Yeah. Okay, so we'll switch this back to cell data. Click on apply. Can we show lift force over this cylinder face with equivalent arrows? With equivalent arrows, I'm not sure if that's possible in ParaView, but I'm sure that you can calculate it. If you're able to do that, then it will be good, but I'm not sure of how to do that. I'll check that, but if needed, I will check that. Yeah. Okay, so far everyone is able to calculate P multiplied by normal multiplied by area, correct? Yeah. Now, okay. Now the next thing that you have to do is integrate these variables, because we want to calculate the coefficient of lift, not the lift force. If you just want to calculate lift force or drag force, you have to only do up to here. Okay. But we want to calculate the coefficient of lift. So for that, we will again go to filter and go to search. Under this, again, type, integrate, variables. Okay. So again, when you click on integrate variables, you can click on apply, integrate variables. And now it will show you in the data sheet set. Okay. So over here, instead of point data, you can click to cell data. So see over here, once you do integrate variable, it will generate the spreadsheet view of just one value. This is at time 0. If I change it to time 49, can apply. These are the values for it. Okay. So make sure in this spreadsheet view, once it generates under attribute, you're again clicking cell data, not point data. Okay. Because we have computed everything for cell data. Okay. So once you have found this integrate variables, so over here you will see that you have lift force, you have the length, you have that's right, you have the normals, and then you have all the velocity and all. Now they all are set to 0. So let's keep this. Once we do the plot data over time, it will all become proper. Okay. So once you have done integrate variables, next you can do is go back to you can go back to calculator directly. So again, you open this calculator. This is the second time you're using calculator. Again, from point data, change the attribute to cell data over here. And this time you can change the name to coefficient of lift. So I'll just name it as CL. Okay. So you can do this for CL. And this time the formula for coefficient of lift will be your force divided by half rho V square area. Okay. So we have force value. We've computed lift force from the previous calculator, that is over here. So we will be able to add that lift force over here in this calculator. So let's add that first. So under scalar, you can see there's something known as lift force. So we added lift force. Then we'll just put it in brackets. Yeah. So you can add the brackets using this button over here. You can use your keyboard as well. So lift force divided by, let's add one more bracket, half. So that will take it as 0.5, half, then rho V. So we have the value for rho. So in case you forgot what was the value for rho, you can go to your control dict. Under the control dict in the functions tab, you had added your rho value. How to add lift force? Okay, 1 minute, I'll just explain this. So in case you forget your rho value, you can add, you can see the rho value over here. So your rho infinite, you've taken it as 1.225. So you can always check it over here, or you can check other files as well. So usually value, if you're simulating for air, you'll take the value for rho as 1.225 only. Otherwise you can always change it depending on how on what fluid you're solving. And for people asking how to add the lift force, so again, when you click the second time the calculator, make sure again you're on attribute type cell data, and under cell data you have scalars, and under scalar lift force will also show up now. Okay. So once you click on this lift force, you can then continue with the formula. So we have half rho. So the value for rho is 1.225. Then we have velocity. So velocity in this case, we've taken it as 1. So we'll just add the velocity over here. Velocity squared. So we'll just add top. So over here, there's this small option to add the power option. So raised to 2. And the remaining formula is area. So again, you can multiply, and then in scalars, you have area. Okay. And you close the bracket. Make sure you close the bracket, otherwise it will throw an error. Okay. So is everyone able to do up to here? After doing lift force, you use the filter integrate variables, and then you use a calculator. Make sure that your attribute type is set to cell data, and then you can rename it to CL and add the formula. So everything is under scalar only, nothing is under vector for now. So you can add this value for scalar. under scalars. Okay, so you have lift divided by half rho v square area. Okay, so once you have done this, you can click on apply. And now if you see, this particular sheet has been updated. So now you'll also have CL. Okay, over here you'll have value for coefficient of lift. Okay, now once you have got this value, now this coefficient of lift is for time step 500. Okay, so at the 50th or 49th second, your coefficient of lift is this, but we want to calculate the coefficient of lift with time. So for that thing, you have to make sure you're clicking this calculator, the second calculator. If you want, you can again rename this to coefficient of lift or drag, whatever you're computing. If you want, you can leave it at calculator. You can go now to filter once more. Yeah, v value is 1 here because it's free stream velocity. You can again check that in your velocity file over here. Okay, that is why we've taken it as 1. Now you can, once you're done with the calculation, the calculator option, then go to again filters, go to search, and this time you will search for plot data over time. Okay, so this one. Before that we had done plot over line. Now we will do plot data over time. Okay, click on plot data over time. There will be this dialog box that will show up. So it will ask you whether you want to do it, because this particular operation, if you have a lot of if you have a large data set, so in case you have multiple files, so in this case we just have around 50 files, so it should run fine. But say you have 100, 200, or even 1000 files, so this will take some time, because it will calculate, or whatever filters you have added, it will add this filter for each time step, and it will give you a graph based on that. So that is why it will ask you whether you want to do it or not, because it will take time. So click on yes, and then click on apply. Field associated, you can click on cells and then click on apply. So you can see over here in the bottom, it will do that. Now over here, it will show the graph. You can again click this graph. I'll close this. And once you click this graph, just scroll down on the left side, and you can switch off everything and only keep CL stat. Okay, so in case it gives you problem on this cells, click to point, apply, attribute type. Okay, okay, 1 minute, we'll do that again. So calculator, filter, search, plot data over time, enter, yes. This time we just click apply. Yeah, that generated a little bit. So over here, we'll switch off everything. Okay. Let's try this once more. Okay, giving an error. plot data over time, enter. So is it showing for others? Can someone confirm? Okay, then maybe mine has some issue. It usually after this thing, it will show you the CL and the CL plot. Yeah, okay then. Okay, fine. Maybe there's some mistake on my end. Okay, I'll check this later on then. Okay, so you get the idea, right? So you can then plot your graph on that. So you'll get a graph something like that. Again, then you can convert that to spreadsheet view, and then you can download the spreadsheet view as you did for plot over line. Similar approach, you can then, if you want, you can keep that plot over there as well. You can take a screenshot and you can apply that, or you can copy the CSV file, open it in Excel and plot it on that. Okay, so this was one way of doing it in ParaView. Okay, the first way was ParaView, second way was Excel. Third way, you can also do the same that we've done using Python. Okay, so I'll show you that. So for now, you can keep it as it is. Okay, that's clear. Yeah. So in the case structure, I'll just increase the size. Yeah. So in the case structure that you have, this one. Yeah. At the end, you'll see that there's this coefs.py. So you have a Python code for this. Okay. So you can type a Python code custom, which will use the post-processing files that you have. So in this way, it is not force coefs. It will be coefficient.dat. So let's cross-check this, whether it is coefficient. So post-processing force coefs 0 coefficient.dat. Yep. Okay, so this is a custom Python code that I had programmed a while back. So in this way, you can post-process the CL, CD, and even straw hole number on using Python code. Okay, so it will require you to assign a file. So in this case, it is going to be reading the post-processing. So in post-processing, you have the force coefs. Inside that you have 0, and then under that you have the coefficient.dat. So you have this file that it will read. You have to define the characteristic length. So in this case, our geometry is 1. Yeah, and then you have UINF, that is your infinite or free stream velocity. In this case, it is 1 meter per second. Then what we're doing in this particular block is we are loading the data. So again, the data that is there in this file, we are saying that time is the first column. So again, this is using like the coef.file. So all of these are written in C. So OpenFOAM is in C. That's why it uses the old numbering style. So you will have 0, 1, 2, 3. So this is column number 0. D is column number 1. Then you have 2, 3, 4. CL is column number 4. So that is what we are doing over here. Time is in column number 0. CL is in column number 4. And CD is in column number 1. Now these three values, not these three, but these two values, CL and CD, the column number will change based on the OpenFOAM version that you're using. So always cross-check with the code, the values assigned over here, and the column that is actually present in your DAT file. Because in OpenFOAM 9, it happens that you have the column time, then you have CD, and then you have CL. You don't have CDF and CDR printed this way. Okay, so always make sure that your folder is properly assigned and you're allotting the proper column in your code. Then after this, once you've assigned everything, you've written the proper columns, you've assigned the file name and everything, you can then go with the statistics. So these are all the calculation part. So over here, you're just going to calculate the CD fluctuation, CD, RMS, and all of those things. So these are just the formulas for it. Then you have over here, I've done power spectral density analysis. So that is why you have this. So this one was for finding finding the FS, the sampling frequency, or the dominant frequency as well. So for dominant frequency, we are using this particular thing, FS. And that is used for vortex shedding and all of those things, because we are also computing the straw hole number over here. Okay. So your straw hole number is your frequency multiplied by characteristic length divided by the free stream velocity. So in this case, frequency is calculated from here. Characteristic length, we've assigned it on top. Same goes for free stream velocity. Based on that, then we start printing the results. So first you will print the values for coefficient of lift, coefficient of drag. You can print the result first, and then you will also have plot. So you can plot CL and CD versus time. So this is for CL, this is for CD, and you also have for PhD. And also there was one more block for straw hole number. So straw hole number, it won't plot it, but it will rather give you the value for it. So how to run this code in OpenFOAM? It's pretty simple actually. So when you've done your simulation, you've got all of the values. So you can, if you sourced it properly, let's do clear. Yeah. So you can type Python 3, and then you type in the file name. So in this case, coefs.py. Okay, so you type Python coefs.py and you hit enter. So this will plot everything based on that data. So over here you can see that it has plotted the CL versus time and your CD versus time. So this is the graphs for it. And if you close this, it will also give me the PhD of CL. So you can also search your dominant frequency and all of those things. So you can program it in such a way that you get all of that data. So this is one thing. So you got the graph, and along with that, I have also made it print the mean CL, mean CD, vortex shedding frequency, that is this, your straw hole number. Now, since over here the length is 1 and the velocity is also 1, so these two terms are almost negligible. So your straw hole number will be equal to the dominant frequency. So that is why your PhD, your dominant frequency, your vortex shedding frequency and straw hole number is exactly the same. And then you also have CL RMS, CD RMS, and all of those things. Okay, so in this way, if you have a custom Python code, or if you wish to compute something from the data that you've already got, so if you've added these in control dict, if you added these functions, you can then use custom Python code to program all of this, and you can then extract all the data and plot them as an however you want. So that in Python, what happens is you get the freedom to program it how you want. You can also print whatever you want, whereas in paraview you saw that we had to do so many steps and then you got one output. So on paraview it is a little bit tedious to do it, but you can also see what you're doing. So that is one thing that is a pro and con of each of these. Whereas in Python code, you have to first know programming. So that is one downside. If you don't know programming, it becomes a little bit difficult. But again, if you know basic programming also, it's fine. Now this code that I've ran, it isn't something really great. It's very simple code programming. You have to just assign some variables in the starting, and then you just load everything off of it. So that is one thing. Yeah, so there are a few questions. We have calculated CL or CD through all those filters. So in paraview, whatever we did just now was just for CL, coefficient of lift. You can do the same for CD. You can just change the lift force to drag force. So instead of taking your normal in the Y direction, you can take normals in X direction. And then you can change the formula accordingly for, I think the formula remains the same for the coefficient of drag. It's just that the force changes. The base or the denominator of the entire equation is the same. Yeah, and another thing that I wanted to show you was, so if you go to the PPT towards the end, there are these two links. So now if you're on OpenFOAM 9 or 2412, you can click either one of those. I'll click both. Yeah. So these are some of the functions that are available in OpenFOAM. So this one is for OpenFOAM 9. So again, if you search on the left hand side, so again, you're in function objects. So these are all the things that are available. So under field values, so this thing that you write over here, right? Wait, my system will become laggy. Yeah. So under the control dict, you, okay. 1 minute. I'll just try to close one tab. Wait, let's close a few things. Yeah, now it's better. So in the control dict, you write this function object library, and then you type this. But what is the significance of it? So that is over here. So under function objects, you have field values and the volume field. So let's see all these. So if you want to ever search what are the function objects that are there available in your particular version, you can go to these websites. So this one is for OpenFOAM 9. There's another one for OpenFOAM 2412. So again, for OpenFOAM 2412, you have all of these classes. So you have momentum error, you have wall heat flux. So for heat transfer people, you can check this out. Wall shear stress also. So if I click one of these, it will give me all the knowledge of what is happening in the back end. Along with that, it also gives me this. Okay, so you can copy paste this entire syntax into your control dict, and wherever it says that you have to specify the patch names and all of those things, you have to specify that, and you can run it as it is. Okay, same goes for CL and CD. So if you see force coefs, you can scroll down, you have the syntax block for it as well. So over here, so whatever is mandatory, whatever is not mandatory, all of those things are there. So these are some optional entries. So if you want to add porosity, you want to add coefficients, so you can add all of those things, but they are not required. The mandatory part that is there, so those you have to fulfill. The remaining can be neglected. So it's fine that way. Okay. So you can check this one. This one is for OpenFOAM 2412. For OpenFOAM 9, there were more. Scroll down. If you cannot find something, you can just search it over here. So let's see force coef, and it will give you over here this. You can click it. Yeah. Okay. I think I think this website is only laggy for my. Okay, fine. Yeah. So you can check in this repository for OpenFOAM 9. I think for 10 or 12 also there might be one. But for OpenFOAM 9 and 2412, these two are there. So if you require any specific function that you want to apply, you can check these out. Okay. The link is all in the PPT. So you can just control click it. I've also sent a PDF version of this PPT. So in case you just want to see those things, you can check those out. Okay. Yeah. So this was about, yeah. And I also promised you guys about sonic foam or the compressible flows. Yes. So again, this is one of the, I think it's the same code that I had. This was Strohal number. This was a little bit different. I also have one particular code for computational aeroacoustics. So there were 2 or 3 people who were interested in that. So those files also there. I will upload that. So that in that you can solve a 1/3 octave, and you can also solve for the spectral values for your sound. So those things are there. So again, those are all programmed in Python. So again, that's why I said that you have more freedom when working with Python. You can add things, subtract things. If you don't require something, you can remove that. Yeah, the GitHub link for aeroacoustics will be, yeah. So I think yeah, it's already I think available. I'll share that once more at the end. Okay, so about the compressible flows. So Pile ma'am, we have time, right?
Actually, it's almost 4:45, and professor is also waiting.
Okay, ma'am.
So
I'll just quickly show this
Mhm.
in 2 minutes, and then
Yes,
we can continue with that. Yeah.
we can.
So for people who are interested in compressible flows, I'll show this for OpenFOAM 2412 because you have more options in that. So under user, you have lib, you have, you can scroll down to OpenFOAM 2412, and tutorials. So under tutorials, you have compressible flows. So the tutorial or the photo that I showed you of the shock wave, so that is under sonic foam, and you can check laminar. Laminar, you have forward step, and you also have RAS, that is prism. So this is the case that I ran and I showed you the output for. So you can run these cases as it is. This sonic foam is quite stable when it comes to other solvers. You also have rho simple and rho pimple foam. Rho simple foam is again your steady state compressible solver. So in case you want to do something with that, it's there. And there are n number of solvers. So again, sonic liquid foam as well. So why I said 2412 is in the ESI versions of OpenFOAM, you have more options when it is concerned to compressible flows. Whereas if you were to open OpenFOAM 9 or 10, it's really sad over there. I'll show you that as well. So it's under OPT. I'll show you for OpenFOAM 9 tutorials, and you have compressible. So you see that there are only 4 options. So you're very restricted in terms of the ORG version. Again, for the newer versions, there are some options. Yeah. So for compressible, there are more options. So if you're interested in compressible flows, you can always check these out. Everything is present in the OpenFOAM tutorials, and there are specific cases on compressible flows as well in a repository, so you can check those out as well. Yeah. So I think Professor Prabhu is waiting, so I think conclude on this. So thank you everyone for listening patiently. Yeah. Payal ma'am, I think we can
We
continue.
can, if there are some questions, a couple of questions we can take.
Okay. Yeah. So Mr. Vinod, the Python code plotting I did show. You can check the video out. It's not a problem because everything is recorded. It's on YouTube also. So in case you missed that, you can check that. Okay. The codes and everything are sent in the drive. So within each of the cases over here, I can show you as well. So this is the case. Yeah. So within this case itself, you have this coefs.py. You can check this code out. Okay. So this is the Python code. Yeah. Any other questions? Yes, Santosh, you can run from any drive. At least I'm not sure if on the newer Windows systems you can do, because previously when I used to do that, I used to keep my data on a hard drive and then I used to run everything off the hard drive. I used to not run anything physically on my computer. So that is also possible. But again, just check with the newer Windows updates. It becomes restricted on that. On Linux, it is possible. If you're on a Linux system, you can obviously do it. Whether you're in a C drive, E drive, or even F drive, you can do everything. You have that freedom over there. Yeah. Yeah. So I think, Payal ma'am, we can go ahead with.
We can start with the
Yes.
concluding presentation. Anyways, if you have any questions, you are most welcome to contact us through our email ID, and we will definitely get back to you. So I have a small presentation to for all of you. We just wanted to let you know how can you connect to us and the next steps after this workshop or this program. So this program is concluding now, but it's like a new beginning that FOSSEE will like to have with all of you. So I'm just presenting my screen. Okay, is my screen visible?
Yes.
Yes, ma'am.
Okay, great. Just a second. Okay, so here are the next steps. So please listen to this presentation very carefully because I'll talk about how can you contribute as faculty members and as students for the FOSSEE project of IIT Bombay. So first of all, I'll talk about how to master OpenFOAM. So during this program, you have learned to install OpenFOAM and also you have learned how to use OpenFOAM to solve particular cases. So now I'll show you our website where there are a number of tutorials that you can refer to. We have a repository of case studies of some solved research migration projects. I'll walk you through everything. Okay, so and I'll also talk about how to stay connected, how to contribute, and everything that is needed. Just a second. Okay, so here is the scope of contribution for the faculty members. So the first of all, faculty members, I would request all of you to guide at least one student from your respective institutions on a case study project. So what is a case study project? Let me explain. So cases are small problems on CFD that can be solved using OpenFOAM. So you can request any of your students or more than one of your students to learn OpenFOAM, and you can also propose them a topic on which they can work, and that topic will be taken as a case or a case study for that student, and that problem in the CFD, which we are referring as case or case studies, can be solved using OpenFOAM. So this case study project, you as faculty members can also publish on FOSSEE.in website, cfd.fossee.in website, and also encourage your students. Okay, and number 2 is the research migration project. So this research migration project is for the students who are doing PhD or higher level research work, and also for the faculty members. So here we are suggesting you to pick up any of the research problems that are published in renowned journals and replicate it using OpenFOAM. So this is a research migration project. I will request all the PhD students here and all the faculty members here to please submit a research migration project that will be in this way, the learning will be better. You will be able to use OpenFOAM in a better way. The third thing is how to contribute to a lab migration project. So in FOSSEE, we always help the institutes who have their lab in proprietary software to migrate it to a free and open source software. Okay, in this case for CFD, we have OpenFOAM. So this problem is actually proposed by the faculty members. So whoever, in your institutes, if you have a lab which are using proprietary software, that lab can be migrated to OpenFOAM, and you will have to propose all the experiments. We have a template wherein you can propose all the experiments that are listed in your lab course, and each of the experiments will be migrated through FOSSEE. So this, for the migration, you can involve your own students, or our FOSSEE team members also can contribute, get involved, and propose the solution for the experiments, and then a whole lab can be migrated to an OpenFOAM lab. Just excuse me for a second. Okay, I'm back. So as a next step, you can also go back to your institutes and arrange for an orientation session. So in an orientation session, what we request you is, you can call all your students and all the faculty members from either chemical engineering, mechanical engineering, and aerospace engineering in a common place, and we will interact with them. We will let them know how to learn OpenFOAM, how to use OpenFOAM in their research problems and in their regular case study problems. So this orientation session, we actually have a norm of a minimum of 200 students and teachers. So this activity is a very easy one. Immediately you can plan for it in the month of June or July, when the new students come, when the new semester begins and the students come in. They can actually attend this orientation session. That will be very useful for them. Next thing, you can also organize a workshop, an OpenFOAM workshop at your institutes. You can invite the students and faculty members from your nearby colleges, and in this way you can also organize such workshops in your institutes. Okay, and the last thing is, and it's a very important thing, is we have developed a course on OpenFOAM. It has already been given to IIT Vellore, and it's a 3 months course, a full semester course, and this course can be included in your institute curriculum, or if you don't have the provision to include it in your institute curriculum at present, you can readily include it in your value added course. It can be any credit course or any kind of value added course, and our team members will take this course for the students of your institute. So this is another option to get involved with us. Okay, and now let me talk about the scope of contribution for the students. Okay, so the students can get involved by submitting a case study. I have already explained what a case study is. The second option is all the students are also invited to publish research migration projects. Okay, they can also enroll themselves in OpenFOAM learning program. So we have a separate program called a learning program, which is which is apart from the regular internships and fellowships that we offer to all the students. So in our cfd.fossee.in, there is a tab called services. So there a form is available. So we will be starting the next OpenFOAM learning program in the month of August or September. I'll announce it on fossee.in as well as in our LinkedIn page. And I already have your all email IDs. So I'll be, whenever we announce this OpenFOAM learning program in our second, in our autumn semester, I'll get back to you through emails. Okay, so this is another thing. So what we do in OpenFOAM learning program is we select some of the students who have a basic knowledge of OpenFOAM and who can be trained by us. We actually select some of the students who have potential in them and who are looking forward to learn OpenFOAM and use OpenFOAM in their regular research work or coursework. So this is about OpenFOAM learning program. Some students are actually very much benefited with this program. Some people want to learn OpenFOAM and they don't afford. They cannot afford to learn OpenFOAM from private resources, and that's why FOSSEE is there to support them through this learning program. And they actually gain knowledge, and when they apply for the summer fellowship or semester long internship for the first semester or autumn semester, they get selected because they gain that expertise to apply and to get through the screening task. This was about the OpenFOAM learning program. Now you can also the students, as students you can also become FOSSEE campus ambassadors of your colleges, and you can also organize OpenFOAM workshops and student orientations in your institutes. So all the student coordinators who are becoming these FOSSEE campus ambassadors, they will receive either a certificate or a written letter of appreciation from the FOSSEE team of IIT Bombay. So this is also a scope of involvement for the students. And the last thing is, there is always, we always advertise for the internships and fellowship. I have already spoken about this. We conduct 2 internships, one for the January February semester and the other for the autumn semester. And once in a year we also conduct this summer fellowship program. So this was the scope of contribution for the students. Okay, so this is the website FOSSEE.in, which is really, we are very sorry, we regret the inconvenience that FOSSEE.in is still down, but I can show you a dummy website of cfd.fossee.in and talk about the resources and how can you contribute. Okay, so let me just show you that first, and then Professor Prabhu will interact with you. So this is a test website. The original website is cfd.fossee.in, which is not available right now, but this is almost a replica of that. So this is very important because all the tabs looks the same here, the upper tabs. So once you click on the resources, you'll be taken to this place where we have listed all the spoken tutorials on OpenFOAM. So these spoken tutorials are audio video tutorials which enables any learner to learn at their own pace. So they are like your live tutors who are teaching you in your institutes. They speak and they write. So actually you can use them to learn at your own pace. And one very important thing while you use the spoken tutorials is you'll have to unmaximize the window while using the spoken tutorials and open a new tab or a new terminal side by side. So this side-by-side learning method is a very useful and effective one for using and learning through spoken tutorials. So here you can learn at your own pace whenever you are available after your classes, and gradually from the basic level you will be taken to the intermediate level, and your learning will be uh, very much effective. Okay, so we also have these installation guides over here. Let me see if it takes me to this page. So we have a number of basic tutorials over here, and also advanced, intermediate level. So these are all basic level tutorials, and we also have 2 intermediate level tutorials. So this was about the resources, and we have a repository of case study project, completed case study projects. So here you can see the college names. These are all the students whom FOSSEE has trained. So this repository is built by the students whom FOSSEE trains. Okay, it is not by the FOSSEE team members or the IIT Bombay students or IIT Bombay professors. Okay, so you can see all the college names and the contributors names. So you as students or you as professors, your names will be reflected here and will be published here in FOSSEE, cfd.fossee.in. And it is very important because this is a government funded project, and the value is immense. And this is a proof that you already know a software and you are applying it to publish a whole case or a whole project by yourself. So in an interview, this thing will hold much more value than a certificate. And obviously we also award certificates to whoever publishes the case study project and research migration project. So after you go through all the spoken tutorials, all the basic and intermediate level spoken tutorials that are listed in the fossee.in site, you please refer to all these case studies, and whichever subject interests you. Okay, you can find many verticals or many subject areas of CFD which are covered in all these case studies. So just select and download. You will be able to download the whole report, the whole case files from this repository. So this is a very valuable thing. Similarly, we have this completed research migration projects and lab migration projects. So after this program, you can go back and explore this maybe a couple of days later when our cfd.fossee.in works properly. Okay, so here I stop presenting my screen, and I would request Professor Prabhu to please interact with the participants. Yes.
Hi everyone, can you hear me and see me?
Yes, sir, welcome.
Yes, sir.
Hi.
So, Professor Prabhu Ramachandran is the principal investigator of FOSSEE team. He is guiding all the verticals of FOSSEE, and thanks a lot for joining, sir. Welcome to this session. And in this program, the majority of the crowd is faculty members, and we have also allowed some students. Some of them are the FOSSEE fellows and FOSSEE, OpenFOAM learning program students, and some students from other colleges also. So this is about the participants in the, and some of them are also joined, have joined using the YouTube link. So all of them can hear you and see you now.
Okay. Okay.
Over to you, sir.
Okay. So, firstly, thank you, Payal, for inviting me to this workshop. And I'll also thank all the excellent FOSSEE OpenFOAM team who've done a great job in these workshops that they conduct from time to time. I hope that all of you have enjoyed the session so far. So I primarily want to talk about a couple of things. I won't take too much time. I know it's a long day. It's the end of the day. I don't want to bore you with some long lecture. So just something very short. I just wanted to discuss. The first thing is I'm very happy to see that a lot of you are interested in OpenFOAM and are participating. This is extremely useful and important because for many faculty members, this may not make a difference, but it makes a big difference for people who are like students. So in the case of students, sorry, is my audio? Okay, fine. Okay. Yeah. So if you are teaching students, commercial tools like say ANSYS Fluent, very often Fluent is offered at a much lower price in an academic institution. But when you go out, when a student graduates and leaves and wants to start, say, a company or just perform an analysis, irrespective of whether they have a company or not, without access to the subsidized version, they are lost. And in fact, it's very, very expensive for many of these open source, many of these proprietary tools. So in this context, tools like OpenFOAM are extremely important, because by teaching them these kind of tools, you are enabling them so that they can, when they graduate, use these tools to do all kinds of things. So it's extremely powerful, and it's a major enabler, especially in a country like India, where not everyone has a lot of money to spend on these kind of things, and it also inhibits a lot of innovation. So supposing the tools that you have to use are expensive, it really inhibits the ability for you to use these tools later on. So by learning OpenFOAM, even though OpenFOAM is generally considered much harder to use, it does provide a lot of good functionality that you can use. And by conducting workshops like this, we hope that you can train your own students in order to use these. Now, so I'm very happy that a lot of faculty members have joined here, but your role doesn't stop here. I really hope that you go back to your universities and you exhort your students to actually use open source tools. And please note, OpenFOAM is just one part. Right? There are many other open source tools like this. And all of these things are available for free, which allow you to use your hardware, your equipment, and do a lot of powerful things with them. Right from the operating system, from editors, using AI, programming, making plots. So I heard people talking about TechPlot, right? But you saw a very good open source alternative in the form of Paraview. So there are lots of these open source tools that are really good, that are used by people who do research and in the industry across the world. It is just that, unfortunately, many people are not aware of them, and therefore they don't use it. So I exhort you to please, instill this passion for open source in a lot of your students, and to also look at various other offerings that are there in FOSSEE and as well as outside of FOSSEE. Okay? Because open source, has the ability to, for students, it allows students to advertise their skills. Right? If they participate in an open source project and make contributions, their contributions are available for everyone to see. So it really improves their job prospects. The other nice thing is, students who participate in things like this, get to meet a lot of like-minded other students across the world. So it improves your friend circle. And of course, there's always the cost advantage and the fact that you can learn a lot more. So I strongly urge you to not just look at OpenFOAM, but please, of course, look at OpenFOAM, but also beyond OpenFOAM to other open source tools that would be useful for you. So if you, for example, have colleagues in other departments who could make use of free and open source tools, or who are spending a lot of money purchasing tools for their curricular requirements or their research needs, if you're able to find an open source equivalent, and it's something that FOSSEE already has workshops for or learning material for, feel free to reach out to us and we'd be happy to help. Having said that, none of this would be possible without your active participation, and none of this would be possible without the FOSSEE staff as well. So again, thank you very much for being here. I look forward to seeing you in further workshops that FOSSEE conducts. And I hope that you will continue to participate and encourage your students to also participate in open source events such as these. Thank you very much.
Yes, thank you so much, sir. And one more thing I would like to mention, that the OpenFOAM team of FOSSEE also is also a very good platform wherein the academia and academia interaction. So there is a scope of academia to academia interaction and also academia to industry interaction, which is very important. We have a group of people from different colleges of India and abroad. Some of you, you have already witnessed that our faculty members those who have lectured for this program. And we also have a group of people from the industry, from the CFD industry, who are our advisory board members. So they also guide our interns and fellowship students. And the faculty partners also, interact with them for their projects, and it's a very good platform for interaction and networking. So please stay connected to us, and there is a lot of scope of working together and taking our careers forward. So yeah, one more thing, I just forgot to mention that Preeti has put the attendance. So if some of you have missed it, I'm just pasting it once again. Please mark yourselves present for this session. And we also will send the feedback form through email, but now also I can just paste it here in the chat box. In the meantime, you can ask if you have any queries, anything, any doubts for our team. Our team is here. You can see Paris, Ivan, Manjil also is here just now. Yeah, that's Manjil. So we'll be happy to answer your queries. So please go ahead. Any query is welcome.
Hello. Yeah, am I audible?
Yes.
Yeah. So first of all, thank you so much, Payal and team, for this wonderful session. Just one thing I would like to ask you all. As you mentioned that FOSSEE is conducting semester-long courses and this kind of session. So, are there any possibilities to get an industry hiring and that sort of things through these programs?
I could hear industry hiring.
Yeah, I mean, once we are trained with this open form and all, so there are a lot of requirements, right? So do FOSSEE have some kind of, network with industry, or do they have some industry partners so that if we are trained properly in open form, so that we will have chances to get hired by them?
Yeah, actually, the hiring process will depend on the requirements of the industry. So, in FOSSEE, what we do is we connect the good interns with the industry people. If they, they float the research problems. From their R&D department, if they have some problem in CFD, they float it, and they actually directly works with the students. And the students are also guided by a co-guide, who is a faculty partner from IIT Bombay, from the FOSSEE team. So, and there is also a mentor, either Ivan or Manjil or Pranay or somebody is there to guide them. So, no, 3-4 people are guiding one person, and person should actually get an idea about not only the technical knowledge of that student, but also his persistency and his punctuality and his deliverable qualities. So, if that industry partner is happy with that intern, they can also recruit that intern. So that way, FOSSEE is facilitating. Otherwise, we don't have any direct, employment channel kind of thing at FOSSEE CFD team.
Okay, fine. Thank you so much. And I really would like to again thanks and express my gratitude to all your team members. They are really so nice tutors, every one of
So
them.
much.
So I really enjoyed first time this kind of session, and a special thanks to the FOSSEE team. They are organizing such type of open form kind of sessions, because now we need to heftily pay for outside courses and all.
Yes.
And a few years back, like 5 years back, that was like a distance reality. But nowadays it is what is getting so much closer and connected. Specifically, the programs FOSSEE is taking care of that. So I'm very happy for that and grateful for all of your efforts. Thank you so much.
Thank you so much, sir. The pleasure is all ours. And sir, may I know from which college have you joined?
I'm from IIT Hyderabad. Actually, I'm a postdoctoral fellow.
Okay, you're a postdoc.
Yeah.
Okay. So
Yeah.
definitely go for the research migration project, sir. For
Yeah,
any
definitely.
just write to us, we'll be happy to help and guide.
Yeah, and actually, I just have started working on OpenFOAM. I did not work with the OpenFOAM in my PhD, but this project specifically demands OpenFOAM expertise. So that's why I'm a beginner. So that's why I enjoyed this session a lot, and the
Okay, all the
tutors
best.
are amazing. Yeah,
For
I'd
any
like to be
support,
in touch with them.
we are just an email away. We'll be there for your support.
Definitely, definitely. I have to actually come back again and again to all the tutors.
Okay.
They are absolutely amazing. Yeah, thank you so much.
Thank you so much.
Yeah.
This appreciation actually means a lot for our team. They actually work very hard, all our technical team members. So yes,
Yeah, actually, they deserve every single word of it because they earned it. I mean, yeah, thank you.
yeah, thank you so much, sir. So Mr. Satyam Shukla has a question. Please go ahead, Mr. Satyam.
Hi, can you hear me?
Yes.
So first of all, thank you so much. I had no idea about this FOSSEE, IIT Bombay, before. And thank you especially Ivan and Paris, I think, for covering all these stuff, because I have always used ANSYS so far. For me, the problem comes with the OpenFOAM is that you can do basic analysis very easily with ANSYS because everything is there in front of your face. When it comes to OpenFOAM, because now mostly I work with the fluid structure interactions, and it is very difficult, very, very difficult to do it with OpenFOAM. This is why we run away towards the commercial software. So I was thinking, like, they already gave so much time of theirs, teaching us all the way from basics to, I would say now we are intermediate in OpenFOAM. So it was really good. But now maybe I was thinking that later, if you guys have time, you can prepare same kind of workshops for fluid structure interaction problems, some transient rotational bodies, like these problems which are difficult with OpenFOAM. So it would be really good, and I would really appreciate it. And thank you, the FOSSEE team, for all your time.
Thank you so much for the appreciation. It means a lot for us. Yes, Mr. Kalyan Chakravarti, please go ahead.
Actually, they did support a lot. So actually, I'm from an ocean engineering background actually. So I'd like to connect more in this with ocean engineering application. Is it in future we are going to developing any application in ocean? Because still, I'm basically mechanical as well as ocean background. So I need more stay connected with you people so that I can do a lot of problems in motion applications actually.
Actually, one of our advisory team members also works in this sphere, right? Dr. Ranjit.
Ranjit sir is from water resources, ma'am.
Okay.
Ocean engineering, maybe Dr. Karan Gupta is much more suited. Yes.
Okay. So I'd like to stay connected with you. So regularly that you have been told that the learning programs is in there, right? FOSSEE learning program. So I'd also be like to join and I'll also give some tutorials if possible. So I need to stay connected with you people.
So this is our website cfd.fossee.in. Please come back after 2 days. We are actually experiencing unexpected problems in this website, so we cannot show you to you right now. So once this is up, please go through all the profiles of our advisory board members and our faculty partners, if possible. And if you have any specific queries to them, we can coordinate and we can get back to you with the answers.
Sure. Thank you. And is there any possibility of all the PDF means all the workshops PPTs we have been shared, right? Means faculties we have been done. Is it possible to share those also? Faculty.
Actually, we will have to take permission from the faculty members. Otherwise, the best thing is we will send you the recordings. So the PPTs are already there in the recordings. You can refer to them.
Okay. Thank you.
So one request for Ivan.
Yeah, for adaptive mesh refinement, I don't think there's a GitHub repository, but there are tutorials on OpenFOAM only. Manzil, there are for AMR, right? Many. Actually, Manzil is the one who works on AMR, so he's more of a specialist than I am on that.
Yeah, Ivan. We have tutorials for AMR in OpenFOAM itself. Tutorials. So. There are also other codes for you can find other codes in the GitHub repository, but in the OpenFOAM itself, we have inbuilt for AMR inbuilt tutorials.
Yeah, and Gino, yes, I saw your email. By Monday, I will share you the files because I don't have it physically on my system. Once I go on Monday to the office, that time I will download everything and share everything. Okay. So I think there were 2 or 3 requests for previous workshop case files and all of those things. So I will share all of those things. Okay. So don't worry about that.
So Gino Chandran was our semester-long intern, right?
Yeah.
Okay. Yes. So one interesting thing I would like to share with all of you. for especially for the students. So you have met all our staff members, Ivan, Manjil, Pranay, Nikhil. So all of them were our interns, either interns or summer fellow. So they have developed themselves and now they are the employees of FOSSEE team of IIT Bombay. So this is also a scope that you grow up in your knowledge and you apply later on. And if we have vacancies, you can be a part of the FOSSEE team of IIT Bombay. So this is a very interesting thing and we are really happy to see their growth.
Yes, ma'am. Actually, I have one more query to ask you.
Yes, please go ahead.
Yeah. So you mentioned about the semester-long this projects or programs. So are they based on some selection criteria and fees and all?
No, fees is not there. The selection criteria is only our, we actually give them our a problem statement, which we call a
Okay.
screening task. So the
Okay.
selection is based on the screening task and interviews.
Mm.
And we don't refer to their report cards or any of their academic backgrounds. The selection is purely based on how well the student is performing in the screening task.
Okay. So whatever programs FOSSEE is designing all the around the year, so they all are free of cost, right?
Free of cost, yeah. And we actually pay them honorarium also, but at present we are not paying them because we actually this honorarium thing is based on the funding issues from the government. So at the present time, as we all know that we are going, the country is going through financial downtime. So
Yes,
we
absolutely.
we have some funding issues right now. So that's why we have stopped the honorarium thing for all the contributors who are publishing case studies and research migration projects. Even for the interns and fellows, we are not able to pay honorarium. But certificates, definitely they'll receive certificates. And the most valuable thing is the publication of their work on the FOSSEE site that they can refer to anytime in their career.
Okay, okay. Thank you. And just for the volunteers, I mean, any of them can address this query. So, are there any plannings to specifically or dedicatedly organize some programs like CFD DM based or some other parts of this open form special cases?
I think yes. If we have that expertise, we'll be happy to give that.
Espe-
But for corporate people, it is actually on payment basis. And if your team has to travel, that expenses of travel, lodging, and food, that also the company has to take care of.
Yeah, I mean, faucet team consist experts from the CFD DM backgrounds or some what do they that
yes, so we
fluid.
do. Yes, sir.
Oh,
We
I
do.
see.
Yeah, we do have industry partners who are working in that, and there are a few case studies we have on the website itself on specialized topics as well. So when, if needed, we usually take all the specialized topics like FSI, even adaptive mesh refinement and moving mesh, dynamic meshing, and all of those things. We take all the specialized topics in the advanced workshop that we have, and that's usually offline in the month of December or January. So that is when you will see most of the advanced topics or complex problems taken care of. Usually in February or March, we have basic workshops all the way up to September and October. After that, we usually have one intermediate workshop and then one advanced workshop. So that is the flow of how we do things.
Okay, okay, yeah, fine, fine. Thank you. That's fine.
So now I would like to request all of you to please switch on your video so that we can take a group photo for this uh, program. So I would request Deepak to please take the photo. So all the participants kindly switch on your video so that we can have a good memory of this program. I'm really sorry I missed to propose the vote of thanks. And let me just share my screen and do it, and then afterwards, after just I'll take one minute to do this. It's a formality, and it's very much needed for whoever has contributed for this program. Uh, okay, so is my screen visible?
Yes.
Yes, ma'am.
So here goes the gratitude part of this program. We are really grateful to Professor Prabhu Ramachandran. He is the principal investigator of the FOSSEE project. Professor Chandan Bose is leading the CFD team of FOSSEE project. We are really thankful to him. Actually, today also he was supposed to join, but some urgent meeting came up and he couldn't join. And we are thankful to Ministry of Education, Government of India for funding this project. We are thankful to IIT Bombay for providing all the resources, the space, everything that IIT Bombay is supporting us for this project. I'm thankful to my colleague, Ms. Usha Vishwanathan, for her guidance. She's a senior project manager and my mentor. And we are thankful to all the technical team members of the CFD team of FOSSEE, Mr. Ivan Fernandez, Mr. Paris Palkar, Mr. Pranay Pandey, Mr. Manjil Situla, Mr. Nikhil Chadnavis. And I'm also thankful to Preeti Guikar for coordinating this workshop in terms of promoting it, in terms of taking your attendance and emailing you. So thanks to Preeti. And from our studio team, I have Mr. Deepak Kumar Jangir and Mr. Kailash Kadu. You can see Deepak there. So I have always bothered him about, during this program a lot. So we are also grateful to all our faculty partners who have delivered lecture in this session. Professor Hari Krishnan from QSAT, Professor Anirudh Kulkarni from PDEU, Professor Naren from Sastra, Professor Dheeraj Garg from SNU Noida, Professor Manimaran from VIT Chennai, Professor Janani Sri Muralidharan from IIT Bombay, and Professor Tushar Chaurishi from MIT EDT University, Pune. So here we are. Now we can take the group photo and conclude the session. I can see only few of you. There are 51 people here now. I can see only our team members and just Professor Vinod and Mr. Vinod and Mr. Jitendra. Please switch on your video, otherwise, we will not have this memory. Deepak, how many of you can? How many of them can you see? I can only see 4 or 5 people who are switched on the camera.
Yes, Kyle. Only 4 people.
Huh.
Apart from our team.
Govind Sharma is saying that he has, but we cannot see Mr. Santosh. We cannot see. Jay Patil also, but how can we not see them? Even can you see them? The people who are saying that they have switched on their, maybe from our side, Google is.
I think on Google Meet you can see max up to 50 people in one time.
We only can see only 4 or 5 people.
So on the bottom there are those 3 dots, no? More options. You can click to adjust view. In that, then you can increase the number of tiles.
Deepak, can you do it? Otherwise, Ivan can take our screenshot.
I will take the screenshot to count of 3. 1, 2, 3. Thank you.
Okay, thanks a lot. So we are concluding the session now. Thanks everybody for joining, and please stay connected. Thank you. Thank you.
Thank you, everyone.
Thank you, everyone.
Thank you.
Thank you.
Thank you, everyone.
Thank you. Thank you, everybody.
Thank you, ma'am. Thank you, everyone.
Yes, Mr. Chandrasekhar, you have raised your hands. Okay. Yes, go on. Yes. Sorry?
I think maybe my mistake.
Oh, okay. Thank you, Kuber.
Thank you for all.
Thank you, Manuel.
Chris, can I end the meeting?
Yes, Deepak sir, we can end the meeting.